for your employees. Both of these are possible. And lots of companies engage the services of IIT in that direction as well. A fourth touch point is where faculty and industry engineers and scientists are on each other's advisory boards to enable a closer conversation between the two of us. So a lot of faculty are on retainer advisory with companies, both multinational and Indian companies, and several company employees are advising faculty research, advising the institute on curricular needs, and several departments have advisory boards. Chemical engineering has a very active advisory board, thanks to Nag, who set it up when he was the head. So that's the fourth touch point. The fifth is where industry wants to work with all the startups coming out of IIT Madras. IIT Madras incubation cell, which is the home of our startup ecosystem, is home to over 300 plus startups. And several of them are in the domain that you may be interested in. So having visibility of the activity in the incubation cell and having a conversation with these co-founders and founders is extremely useful and fruitful for a lot of large industry, primarily because it's hard to be that nimble and trying out ideas that a startup would probably take on themselves. So this is the fifth touch point. The sixth is where we work with over 80 plus companies through their CSR programs, corporate social responsibility programs, to create win-win-win situations for all of us. In other words, CSR by law has to be spent outside your institution. CSR by law allows that it can be spent on research. It doesn't need to be buying benches for a local primary school only. That money can be spent well on research, creating centers of excellence in an area that is adjacent to where you want to be, and where you see your company benefiting from a broad pool of knowledge, institute benefiting from having an asset on campus and some activity associated with it, and the society benefiting by all of this IP being in the open domain. So we have over 80 companies last year have invested over 110 crores or so of CSR during this last financial year, primarily in this direction of enabling student and faculty activity. So those are the 6 touch points. Please come on board, whichever one appeals to you. Manu can, I'm sure, talk to you about all of them. He's been the head of placement. He's now the dean of ICSR. He also, I'm sure, runs other master's program. My colleague Kaviraj is also there. Kaviraj is part of the Office of Institutional Advancement. He leads our CSR engagement with companies. So you can touch base with any of us and we'll be happy to help. Thank you all for coming, and I look forward to the day.
Thank you, Professor. I would like to invite our Dean ICSR, Professor Manu Santhanam, to address the gathering.
Okay, very good morning to all of you here. I'm Manu Santhanam, Dean of Industrial Consultancy and Sponsored Research at IIT Madras. And this event is being organized as part of our 50th year celebrations of IC&SR. The idea was to have interactions on a department scale to ensure that we have maximum coverage of the industries that are interested in specific areas of research and academic collaboration. This is, I think, the 7th in the series of events that we've been doing with various departments. And it's indeed nice to see such a large participation. Our original venue was, of course, the ICNSR auditorium. But because of an event this evening involving the Chief Minister, we've had to reschedule this event to this terrace hall. But I think this also gives a very nice ambience in terms of being able to directly interact with our research scholars who put up these wonderful posters, and also probably a little bit more of a discussion type of a venue, because the program that has been outlined by our colleagues from chemical engineering is mostly dealing a lot with panel discussions. So I think this may be a better venue in that sense, okay? Or at least we can tell ourselves that and be happy about it. In any case, I welcome you all to IIT Madras. I'll just give a brief glimpse of how industry interactions happen at IITM, so that something to build upon what Mahesh has already said. But this is from the perspective of industry, academia, collaboration in terms of research and sponsored projects. So IIT Madras was established in 1959, currently has 16 departments. A 17th department on medical science and technology was recently started. We expect this to really grow into a very large department with a lot of cross-disciplinary research happening. Many of you may be aware that IIT Madras has been ranked #1 in NIRF rankings for 7 consecutive years ever since the ranking started. And in the last 4 years, we've also been ranked #1 overall, not just in engineering. In the QS rankings in the world, we are around 250 currently, and several departments in the institute are ranked quite high in terms of subject-wise rankings. Now, IIT Madras engages in different types of projects. Some of these are obviously the academic research projects that lead to publications and patents. Those are obviously the cornerstone of any academics research. But we do a lot of work which is translational, tackling global challenges in manufacturing and construction, telecommunications, space, defense, environment and water, and energy. Much of the discussions that you'll see later touches upon all of these domains, which are extremely well attended to by the faculty members in chemical engineering. Transformational research, having direct social impact, is also a major initiative at IIT Madras, and disruptive improvement in housing, water, healthcare, education, and energy. Many of our projects touch these areas in many different ways. We have a very good industry collaboration. More than 1,500 projects are ongoing with industry, with more than 600 Indian companies and more than 80 foreign companies. We've been annually filing more than 200 patents, and we expect this number to continue to grow as the patent awareness becomes a lot more widespread among students and faculty. Now, industry can collaborate with IITM in very many different ways. There is a lot of flexibility in the way that industry collaboration can happen. The first one is off-the-shelf solutions, which are looking at the expertise already available within IIT Madras, short-term projects where we attend to industry problems and help them get over these problems in a rather quick period of time. The other one is research-based industrial projects. Here, the idea is to work together on a problem that is of interest to the industry, but has significant academic potential also. That helps us look at involving PhD students to solve these problems and take the problems over a longer period of time, and hopefully look for some joint collaborations and patents. Retainer consultancy, as Professor Mahesh already touched upon, is something where the industry essentially seeks the advice of the faculty members, not relying on any laboratory usage or any facility usage in IIT Madras, but just sort of picking on the brains and getting the faculty member to interact directly in the industry and advise them on various matters. CSR, again, Mahesh touched upon it quite elaborately. And these are essentially looking at projects for social development. But these days, a lot of CSR is also coming in for fundamental research, which can have a significant social impact. Research centers are often created with large support from the industry. There are state-of-the-art research facilities, centers of excellence that have been created with the help of a lot of industry partners. And industry also sometimes sets up endowed chairs in departments, which look at promoting faculty members that are doing focused research in the areas of interest of the industry. Our industry collaboration what that was. Anyway, yeah. So industry collaboration has been increasing steadily over the years. Last financial year, we touched more than 250 crores in industry funding. This year, I'm happy to inform that we have already touched more than 450 crores in industry funding, and this number is growing steadily because our involvement with industry is now going on multiple different levels. Some of examples of our transformational research, you may have already come across these, of course, our involvement in 5G and the Shakti microprocessors, the Neobolt indigenous motorized wheelchair vehicle. These are all innovations that have been in the news lately. We've been also setting up several centers of excellence to address all of these important global challenges. And many of these have global perspectives also. Some new centers of excellence that were recently initiated are given here in terms of water management, DRDO Industry Academia Center, Hyperloop, Affordable Housing Accelerator, Global Water and Climate Adaptation, and so on. We also are recognized as an institute of eminence by the government of India. And as part of this, there's a very large research grant over a period of 5 years. IIT Madras is the only institute amongst all that have been selected as IOE institutes in the country to come up with a plan for engaging research centers to do world-class research and come up as leaders in their respective fields in the world. So there were several sectors in which nearly 70 projects were actually initiated in the first phase of this IOE initiative. You can see that they touch all possible research domains that are current hot topics. And many of these are, involving people from chemical engineering, as you'll see later in the discussions. And out of these 70 projects, 15 new centers of excellence were created in 2023. And it's expected that these projects will lead to world-class facilities being created and put really IIT Madras on par with some of the best universities in the world. Now, I already talked about IP, that we've been filing significant numbers over the years. The aim of our current director is to touch the figure of 1 patent per day. So that is something which is a dream, and we hope that we'll get there. There is increasing awareness amongst students and faculty. We only need to create a lot more of this to really ensure that we can get on to meet that particular target. We have a full setup in terms of intellectual property management. We have an IP cell, an IP marketing cell or technology transfer office. We have a legal cell, and we have an empaneled team of patent attorneys and consultants who help us draft these patents. The entire patent management process is taken care of by our office. There is a lot of interaction with the faculty and the other inventors who come into our office and engage in discussions about their inventions. The idea is to ensure that there is very little time that needs to be put in by the faculty. Our team essentially does most of it. And we ensure that the entire funding for the Indian patent is taken care of by our office so that faculty don't have to worry about even renewing their patents on an year-wise basis. And in terms of international filing, there's a sharing between the faculty or inventor and the institute at 30 to 70 ratio. That means bulk of the funding is still given by IIT Madras. Now, IITM has been recognized for its excellence in IP by the Atal ranking of institutions on innovation achievements. We also recently got, in the last academic year, we won the National IP Award 21 and 22 as top academic institution, and also the CII Award in 2022 for best patent portfolio amongst academic institutions. We have, as I said, an in-house legal team that helps draft the agreements for industry collaborations. These are some examples: non-disclosure agreements, joint development agreements, and licensing of patents. Licensing is an activity that we expect to pick up in a very large way, because this is something where we are really falling short of the leading universities across the world. And here's where we are putting a lot of effort now. In fact, today we have a team from our technology transfer office with a list of patents from the chemical engineering department for all of those who are interested. They are set up on the right side there. And you can also get a glimpse of what patents are there. They've also prepared flyers for these patents, which can help you identify or take a look at patents that you're interested in and follow up on those. This is something that we expect will grow a lot more in the future, and we are putting all our efforts to get there. Of course, there are other non-monetary benefits of IPM, IPR awareness. We also support incubation, student incubation on campus is being supported. And we also help provide industry connect. Now, as far as entrepreneurship ecosystem is concerned, as I said, within IITM, the student groups or inventors who are working on specific projects are supported internally. Especially students have a very good level of support. But by the time they actually start uh, engaging larger with their research ideas and trying to promote or bring up startups, there is an IIT Madras incubation cell that is set up in the research park that helps in the incubation of these companies. We also have technology-specific incubators like the Rural Technology Business Incubator, the Bio Incubator, the Health Technology Innovation, as well as the Cyber Physical Systems Innovator or Pravartak. All of these are set up in our research park, and they are really engaging a lot with our inventors to take their ideas to the next level and help them set up these companies as startups. And after they also set up, there's various ways in which we provide support to the startups to ensure that they are well on their path to excellence. You can see the makeup of our startup hub at IIT Madras Research Park. You can see that nearly about half of the founders of these companies are belonging to outside IIT Madras. So that means this innovation hub is not just for IITM inventors, it is also engaging with other inventors in the state and the country to provide a unique platform to really develop their ideas into path-breaking technologies. You can also see the kind of industries or kind of domains in which our startups have been set up. And many of these domains, as you'll see later, are directly connected with the work that is being done in chemical engineering. IIT Madras Research Park also gives space for industry to set up their offices and research facilities and engage very closely with IIT Madras faculty. And many companies have actually set up their offices there. You can see a lot of these world leaders who have set up their offices. A lot of startups which have actually become unicorns have also been initiated at IIT Madras Research Park. We expect this number to keep growing as more and more awareness is created about this unique ecosystem of it. IIT Madras, of course, is the first institute in the country to set up a research park, and we are really proud of this achievement, and we expect this to continue to grow in the future. So I thank you all. There are various ways of connecting with IITM. We are on social media, and of course, you can also reach out regarding any of the industry activities to the Industrial Consulting and Sponsored Research Center. We are also available, as I said, on social media. You can connect with us in very many different ways, or you can individually reach out to faculty members whose work you find interesting. If you look at our ICSR website, we have details of all faculty members with respect to their expertise, and you can connect with specific people whose work you're interested in to pursue collaborations with your industry. So thank you all for coming again, and I hope you have a day long a day worth of very productive discussions. Let's hope that this grows into a much bigger, the chain continues to grow further as we go along in the next few years. I really want to commend our chemical engineering colleagues to choose this name chains, and the expansion of that acronym was also really very good. I believe that this is the way forward. The chain has to continue growing in the future. So thank you all once again, and welcome once again to IIT Madras.
Thank you, sir, for giving us an overview about ICSR, our dreams and the future plans. And now we move on to the speech segment. So it's my pleasure to invite Professor Ravi Krishna, Head, Department of Chemical Engineering, to address the gathering.
Thank you. On behalf of the Department of Chemical Engineering, the faculty, staff, students, I welcome all of you and thank you for agreeing to be a part of this event. So today's program, in my opinion, is a curtain raiser for a series of periodic engagement that we hope will happen because we need to interact for various reasons. And some of those reasons we will possibly discuss over the course of today. And it goes just beyond interaction for research and productivity. It also goes to the creation of human resource, development of human resource to serve the needs of society, technological needs of society. And for this, I think we need close interaction with the industry to see what is needed in the near future. So I think that is one of the objectives that we have envisaged for this meeting. So this has also been, I think, discussed in other forums. So a few months ago, there was a meeting with the Indian Chemical Council Southern Region in Chennai, where they discussed interaction between industry and academia and the various challenges that it poses. And I think hopefully we can identify some of these specific issues that pertain specific to the chemical process industry and the associated industries, so that we can both forge together a common pathway for to benefit both of us. So, and this, to do this, at least I think the platforms of this nature are necessary, and at least we should not have a constraint in terms of opportunities to meet. So that should be the least of the constraints. So hopefully we can have many of these events together. In today's program, we have kept the interaction in a non-pedagogic manner. So there will be this is probably the second last speech today. So it's more of an interactive panel discussion mode, where hopefully to foster more interaction, discussion. And I encourage all the people present, students and the people from industry and the faculty, to interact to the extent possible in this venue. So it is kind of open venue, so as against the previous one. And so before we go on to this thing, I would like to thank the ICSR staff for making a last minute change, all the arrangements over the last 20 hours or so. Yesterday around noon, the change of venue was announced and everything was in place by 8 o'clock this morning. So I think thanks a lot for the staff, for ICSR to handling everything, and also thank the department. We had a committee, Professor Pushpavanam, Professor Kannan, Professor Himanshu, and Professor Vinu, who were coordinating all the program, who made the program, who coined this name, and also the format of the event, everything. The groundwork was done by them. So big thanks to them, and a large number of student volunteers who arranged the mobilized students for the posters and the exhibits, and we'll see them in large numbers here. To thank all of them for their work as well. So we come to the next part of our program. Gives me great pleasure to introduce our chief guest, Mr. Parag Chipe. Mr. Parag Chipe is the Chief Engineering Officer and Executive Director of Engineering at ThyssenKrupp Industrial Solutions India. He's been with ThyssenKrupp India for the last 29 years. He has a bachelor's degree in chemical engineering from IIT and a master's degree in process engineering from TU Hamburg, Germany. In his earlier days at ThyssenKrupp, he headed the company's process systems design and mechanical departments. He's also been involved in technology development of the company's core competencies of caustic soda, chlorine, fertilizers, refineries, inorganic chemicals, and cryogenic storages. He's regarded as an expert in the group's membrane cell electrolysis technology that forms the basis for the alkaline water electrolysis utilized in the generation of green hydrogen. He widely participates in many industrial forums and roundtables, and is a member of the Academic Advisory Board of Chemical Technology undergraduate program, Shivaji University, Kolhapur. So thank you very much for accepting to be part of this thing, and I now invite you to address the gathering. Thank you.
Good morning. I hope I'm audible. Let me first start thanking the organizers of this event, Dr. Santana, Professor Pushpavanam, also Dr. Ravi Krishna, for having me here, and also not to forget Mr. Sambamurthy, a good friend of mine who actually initiated this. Since the gathering is of chemical engineers mainly, as I understand today's day, let me first congratulate all the chemical engineers, the budding chemical engineers, those who are working and those who are retired as well, for contributing immensely to the field of chemical engineering and contribution to the world. Because I think chemical engineering plays a very vital role in all the developments all over the world. All the materials, be it plastic, be it paper, everything is produced using the knowledge of chemical engineering. Not just that, but I think chemical engineers are going to be responsible to make this world livable, sustainable by means of developing sustainable technologies in the area of green hydrogen, ammonia, and so on. So as we change or transition in energy from conventional, non-renewable type of energy sources to the renewable one, I think chemical engineers would play a very important pivotal role. So we should all be proud of being part of the chemical engineering, and especially to the young students who migrate towards IT. I think this field has a lot of potential in the years to come. The Indian chemical industry, which is more than $200 billion in terms of its volume, in terms of its valuation, is the sixth biggest chemical industry in the world. And we contribute to India GDP to the extent of about 7 to 8%. So that's a fair bit of contribution, and we definitely should also be proud of that. Having said that, we in India have very low per capita consumption of chemicals, petrochemicals, plastics to the tune of only 10 to 15% compared to the developed countries, which means that there is immense potential in future for chemical industry to grow as we continue. So my first message is, this is a good industry to be in. It has potential to grow, and we really make this world livable, sustainable, and keep it in the shape it is today for the generations to come. So that's, I think, a very important role we play. As I go towards my second message, I just want to touch on the history, how the chemical industry evolved in India. So we started with a pharma-based industry. Bengal Chemicals was one of the first big industry to come up. And after World Wars I, II, there was scarcity of the pharmaceutical products in the country, and that's how the pharmaceutical companies first grew. Companies like Jandu, Cipla, Hindustan Antibiotics, and so on. Then post-independence came the development of the basic chemicals industry, the production of acids, alkalis, which is the base of any chemical development. So those industries came. In 1960s, the industry was based on alcohol and derivatives coming from alcohol. So a lot of molasses was then put into alcohol generation and the industry based on that. Then came the era of cracker and the cracker-based industry, wherein the companies, although we don't like this name, Union Carbide, they were among the first ones to start with the cracker. Then companies like Nosil, IPCL, they came up with crackers, and of course then crackers grew, and big size crackers came in by also the private companies and the government companies. So the industry kept growing on various bases in the years which happened. And most of the concentration of this industry happened in Maharashtra, Gujarat, that area. That's really the base of chemical industry. Of course, it grew also in the other parts of India, and it also went to the east, north, and south, but west predominantly had a pivotal role in the development of this industry. Refineries also grew from capacity of 5 million metric tons per annum to today we are at 250, and thanks to the contributions from IPCL, BPCL, IOCL, and the private companies like Reliance and Nayara who contributed to this. Now, why I said this, in all this journey of development, the role of our R&D in developing technologies was not that high. Most of the technologies in the early years, they all came from abroad. Companies in the US, companies in Germany. Germany was quite pivotal in bringing technologies to India. And post-independence, government established the Center for Scientific and Industrial Research. Also NCL, National Chemical Laboratories, were developed, and the whole research went in that direction. The development of process technologies went to these NCL units predominantly. As a result, the development of technologies from the academic institutes probably did not take as much speed as it has in the other countries. I studied in Germany, and I can say that there this collaboration is even much more because there are no NCLs in between. So the second message is, as we go towards the green technologies and we talk about sustainable world, green hydrogen, green ammonia, e-methanol, and so on, these technologies today are not able to produce these products at a commercially viable rates when you compare to the conventional technologies. For example, the cost of green hydrogen, what you produce, is maybe 450 to 500 rupees per kilogram compared to 150 to 250 rupees per kilogram using conventional steam methane reforming technology. So there is a big potential for development to happen in this area. I was happy to see some of the posters which talk about development in alkaline water electrolysis or PEM or fuel cells. That definitely is something which needs to boost. We have a big talent in India of people. We have abundant natural resources available in the form of sun, wind, hydel. So we can actually be even a net exporter of energy all over the world. So it has tremendous potential, and this academia and the industry collaboration can contribute in how we make these technologies commercially viable. Other than that, there could be few things which industry and academia collaboration can look at to make the young engineers coming out of the academic institutes even more, in quotation mark, industry ready, to bring the practical aspect of industry even when they are studying in the academic institutes. And in that direction, few things which could be done is that every lecture, what we have, every subject, what we have, be it chemical reaction engineering or mass transfer, heat transfer, how can we connect that theoretical lecture with the industry by means of guest lectures from maybe the alumni, which is there. I think there's a big alumni, not only in IIT, but other institutes, how they can, for each lecture, make this industry connect. So we should have that lecture connected to industry, which brings the practical aspects of how application of that subject is done in the student's mind, and they are even more ready to come into the industry, step into the industry. Second thing which can be practiced, I understand it is practiced to some extent, but even more, is how the thesis, master thesis, as well as the project work, the final year project work in the bachelor state can happen together with industry collaboration. So projects in industry which are executed in industry to have win-win situation for both industry and academia. I know it is not so easy to get there, but I think a good amount of marketing by the institutes and good amount of approach via the alumni from the industry can make this happen, because it is definitely a win-win. We at ThyssenKrupp Industrial Solution have undertaken a program where we have 2 master students from NICMAR who would come into our company to do their thesis. We will define a problem for them, and we will solve that problem with these students. So that will help in making the bridges between this. So that's the second message, that there is scope for research and development further, especially in green, and we can make the engineers industry ready in that sense. Third message, and this is a question which I'm asked whenever I'm going to the educational institutes, that what do the industry expect from the young engineers coming out of the educational institutes and getting into the professional career, what they have. And I reflected on this question by myself when I joined the industry in '93 as a young chemical engineer, as a trainee in ThyssenKrupp Industrial Solutions that was called UDE during that time. And what did my bosses expect from me, and how today as a boss I expect from the engineers to come. And I have put down in the form of C, alphabet C, which you can probably reflect upon the young engineers when they come into the industry. The first C is very uncommon, which is common sense. We are not expecting in industry all Isaac Newtons to come and define or challenge the existing system. And even as great people like Isaac Newton, and you might have heard this story, that in his laboratory, when he was working, he used to get disturbed by a cat and a small kitten. They used to bang on the door and he used to get irritated. So he made in the wall, connecting to his laboratory, 2 holes, one for the cat and the second one for the kitten. But he found that the cat and the kitten would come through the same hole, one big hole. They were two not necessary. So sometimes common sense could be missing even in the minds of great scientists. Second thing which is expected is curiosity. Curiosity is something which is highly important. And if you look at a small child, the curiosity which he or she displays, and because of that curiosity, the speed at which the learning happens is phenomenal. So as the students come out of the university, go into the industry, this curiosity like child has to be demonstrated. What I see most of the time that people, when they come in the industry, they look at how things are done. If I'm designing a column, a heat exchanger or reactor or P&IDs, how we do these things, what are the procedures, etc. Now this how stops the curiosity. How is important, but not the only important thing. The question why should come in the minds of the student. Why we do things the way we do in the industry. Because we, working for 20, 30 years, probably are biased in the way we do things. And the fresh thinking coming from college can challenge that when they ask themselves question why, and ask their seniors the question why. So this curiosity is expected as well. Third C is the cost. And my boss used to say that engineers are first economists. All their actions, what they do, they draw on paper, they design, everything is converted to money, and finally industry runs to be profitable. So engineers have to be cost conscious. And this thinking has to develop in the minds right when you are in the college. When you talk about a pump, a mechanical seal, a pump with mechanical seal versus pump with the gland pack, how much difference would be the cost? A ball valve versus a gate valve, and so on. There are many examples. So this curiosity and cost consciousness is third C, which is expected to be successful. Fourth C is chemical engineering basics. When I was in the college, I used to write exams of 3 hours, solving 10 questions. And questions used to be such that you solve the problem in heat transfer for 4 pages and come to a final answer. And that numerical value of the final answer and its correctness had a big role in deciding how many marks do I get on that particular question. When I studied in Germany, for the similar subjects, we used to have only 1 hour examination with 10 questions. And the emphasis there was only on the basics. For example, if there's a heat transfer paper, we used to be asked only to derive an equation which governs that heat transfer system and stop there. Don't solve that equation. There are solvers available in the computer to do that job. But to derive the equation, find the equation which governs that system was what more emphasis was given on. So the basic part really as students, maybe you should be focusing on than only the details. Fifth C is communication. And this is also an area which doesn't get its due importance when students are in the university. But the communication plays a very important role, the written, the verbal, and depending on the industry you are in the industry where I am, which is consulting companies, communication is really, really important. We just produce documents which are used by people. We run contracts wherein a lot of money is at stake. So how you communicate, how precise you communicate, how clear you communicate is very, very important. The 6C is commitment. This is especially important for the Generation Z. And I know that work-life balance is important, but the initial days of your career, I think high level of commitment is what industry expects. Commitment in terms of not just the work hours you put in a day, but commitment in terms of longevity of your stay in the organization. If you hop the jobs every 1 year or 2 years, that commitment is not visible. So you need to stay in a company at least for 4 or 5 years to understand the business, what it is, and that benefits you as well as for the company. The last C is the customer focus. When you are working in an industry, you are working not for yourself, you are working for the end customer who is paying for all that. And this customer focus, that attitude that I need to serve the customer has to come in the minds of the young engineers. So these are the 7 C's which I had been propagating as expectation of industry from the young engineers who come into the industry. Thank you very much for your attention, and I wish you a good day of interactions and lot of knowledge sharing. Thank you.
Thank you very much for that enlightening speech. I think a lot of these points, I think, are continuous things that need to be discussed again and again and reinforced all our students and ourselves. So because we are the people connection for that. So I request Professor Pushpavanam to give a memento to our chief guest. So we come to the end of the inaugural program. So we'll take a coffee break now, during which time I think I will encourage you to also look at some of the posters and interact. We're supposed to finish at 10:15. We're running a little late, so the next session, the 4 sessions start now. The first 2 of the sessions will start at 10:45, the first of them. It is a session on sustainable chemical process, moderated by Dr. Vinu. So we'll start that around 10:45 or so. Okay. Thank you very much again. There's coffee and refreshments served there in the back. Feel free to move around.
Hello.
Hello.
Hello. I
Hello.
request everyone to get back and assemble. We are going to quickly start the first panel discussion. Request you all to quickly have your coffee and get back. If you have taken your coffee, you can also be seated and have your coffee and go through the session. Adam. Students who are standing at the back, if you can occupy your seats, that'll be great. Get started. Okay, we'll get started. So let me welcome the panelists for the first session that's going to be on sustainable chemical processes. It's my pleasure to welcome Mr. S. Venkatraghavan
From Tirumala Chemicals. Please welcome, sir. Mr. Mahesh Kapre. Professor R. Nagarajan. Dr. Amit Rastogi.
Dr. Swapna, and Mr. Prasanna Kumar from Tube Investments. Sir, you can see, you can be. So I welcome all of you after the refreshing coffee break for this session. This is going to be on sustainable chemical processes. So as you can see, we have an empaneled set of speakers, industry stalwarts, as well as our own faculty. And we are going to be discussing on very important topics that is related to sustainability, but something that is very close or in simple terms related to energy efficiency, waste minimization, waste valorization, resource recovery, and process intensification. And without much delay, it's my pleasure to first introduce all the speakers, all the panelists who are lined up here. So first, let me start with Mr. Dr. Amit Rastogi, who is the Executive Vice President of Technology at Coromandel International Limited in Hyderabad, received his BTech from IIT Kanpur in 1985, PhD from Sunny Buffalo in 1991, both in chemical engineering. And he has had good stints in Shell, Hindustan Unilever, and Hindalco in various roles spanning from R&D, manufacturing, and projects. He's leading currently a team of about 30 people working in different places like Vizag, Hyderabad, and Mumbai, involved in the development of new fertilizer products, fertilizer production technologies, and plant nutrition solutions. And he has represented Coromandel in various advisory and expert committees constituted by the government in various fora. Next, Welcome, sir. Next, I would like to invite Dr. Swapna Singaraba. Swapna needs no introduction to our own department, faculty and students. She's an assistant professor in chemical engineering department. Prior to IITM, she has worked at National Energy Technology Laboratory in the United States and Imperial College, London. And she has been working in various topics related to carbon capture, utilization, and sequestration. She leads an active research group here, and she's also teaching a course on carbon capture and sequestration, the first of its type in IIT Madras. Welcome, Swapna. Then we have Mr. Prasanna Kumar. He's basically an executive associate vice president at the Corporate Technology Center of the Tube Investments of India. He's a mechanical engineer from Sastra University, and subsequently he did his master's in industrial engineering at Tennessee Tech University in 1996. Spent about 18 years at Eaton Automotive in Michigan and North Carolina in diverse portfolios, including operation, project management, supply chain, and engineering. Holds a Six Sigma Green Belt certification. And at Tube Investments, he takes care of product and business development and also heads the sustainability initiatives of Tubes. He was instrumental in developing and heading the India's first high volume automotive glass lens manufacturing unit for car cameras, which is also an all-women shop located in Sri City in Andhra Pradesh. Welcome, Mr. Prasanna. Then we have Professor R. Nagarajan. He's an alumni community chair professor in our department, chemical engineering. He obtained his BTech in 1981 from IITM, PhD from Yale in 1986. He has had diverse stints in the industry. He served as a research faculty, first in West Virginia University in 1988, and until 2003, he was a senior technical staff member with IBM Storage Systems Development in San Jose. He's been a professor at IITM since 2004, and notably, he was the first institute's first ever Dean of Alumni and International Relations. And during his tenure, he was instrumental in increasing the fundraising from alumni and corporates by about 150 times, up to 15 million USD. He was our previous head of the department of chemical engineering, and he's an expert in ultrasonic process intensification, clean room processes, nanotechnology, and recently he also works on nano emulsions for medicinal applications. Welcome, Professor Nagarajan. Then we have Mr. Mahesh Wagle, who is the co-founder and director of Cybernetic Technologies in Pune. He's an IITM alum from mechanical engineering, subsequently obtained his master's from University of Buffalo in New York. He's a passionate engineer, and his vision made him co-found Cybernetic Technologies as an automation company at a time when the automation market in India was still at an early stage. He received the Distinguished Alumnus Award of IIT Madras in 2020. He's been instrumental in developing many path-breaking processes, such as shear spinning machine for titanium tubes, equipment for copper tea, chemical milling lines, and so on. And he's also focusing on novel supercritical extraction plants for the bioenergy stream in India. Welcome, sir. And we have Mr. Venkat Raghavan, who is the president of Food and Ingredients Business at Tirumala Chemicals Limited. Holds a master's degree in technology and business administration, has around 32 years of experience in the chemical industry in various roles spanning from R&D, technical services, marketing, and business management. Has worked on several projects, including phasing out of ozone depleting substances under the Montreal Protocol and on clean development project under the Kyoto Protocol. He drives several corporate initiatives at Tirumala Chemicals in his role. So welcome, sir. So without much delay, let's quickly get into the topic of discussion. So it is sustainability in chemical process industries. And as you can see, we have our panel who is who has really a lot of expertise in a wide range of chemical process engineering segments, starting from agri to fertilizers to something like supercritical extraction to process intensification and CO2 capture and utilization. So let's start the discussion with you, Mr. Venkatraghavan. At Tirumala Chemicals, I mean, the industry itself is a leading producer of platform chemicals, like phthalic anhydride, malic acid, and so on, which are the key building blocks for a number of dyes, pigments, plasticizers, and polymer industries. And how do you see sustainability getting knit and woven into the different walks of the product life cycle at Tirumala? And how do you see your R&D units help improve the efficiency of the processes, both in terms of maximizing the energy efficiency as well as minimizing the waste, minimizing the use of water resources? And it'll be great if you can throw light on that, and also how you think this academic collaboration will really help you strengthen your goals.
Thank you very much, Savino. Thank you for inviting me into this panel discussion. At Tirumala Chemicals, we produce a product called phthalic anhydride, and the process is partial oxidation process, which where we burn orthoxylene in a reactor at high temperature, produce in presence of a catalyst to produce phthalic anhydride. The phthalic anhydride process is highly exothermic, produces enormous amount of heat. So we take out the heat in different stages, and we take it, generate the steam from the heat, and also use it for processes within our factory to produce other products which are heat intensive in terms of production. So the phthalic anhydride is the mother plant that drives energy for the other plants that we have within our complex in Ranipet. So we have malic acid, fumatic acid, esters, and some fine chemicals. So all of them need energy, and this energy is provided by phthalic anhydride. So in a way, this process is naturally sustainable because it produces heat, and therefore, if we generate our own energy, we don't take anything from the grid. So therefore, we produce about 5 megawatt of power within our complex from the waste heat of phthalic anhydride. But this is how is business as usual for any phthalic anhydride plant. But despite the fact that we have free energy, we embarked on what is known as a process when ESG was not mandatory. We embarked on a process to reduce water. Our chairman himself was responsible for driving this change. So we started reducing steam consumption and water consumption throughout. And a few years back, we installed what is known as a air-cooled condenser, which reduced the water footprint from 4.5 to 5 tons per 5 tons of 5 KLD of water per ton of products to something like 3.5 KLD per ton of products. So continuously, we have come down on water consumption by more than 50% in the last 10 years. So I think I presented this to the Swedish ambassador. He was like amazed, and he even wanted to actually visit our plant but because of COVID, he couldn't make it. But it's something that is the heart of many people. And in terms of R&D, your second question, we developed a process by which we were making malic acid in a batch reactor. We are now producing it in a continuous reactor where tremendous amount of savings in terms of energy, in terms of capital costs, because it runs on a titanium reactor because it's very corrosive at very high temperatures and pressures. So we developed our own process. We tested at a lab scale, then moved it to a 0.5 ton per day scale, and then 2 tons per day. And we are running this process on a 20 ton per day scale. And we also applied for a patent, and I mean, I'm glad to say that we received the US patent last week for this process. So ESG has is well knit in our system, more as a voluntary commitment. Now it has become mandatory. I think there are other speakers who will talk about it in this panel. So this is how we have worked on these initiatives. We also got IIT to one of the IIT's incubation centers, the ICCW, in the research park. They have visited our factory. We've worked on some water production. We are looking at some studies to do, and I'm sure we will do it over a period of time. Thank you very much.
Thank you, sir. So next, let's slightly switch gears and let's hear from Dr. Amit Rastogi, as a leading agri-solution provider in India, focused on, I see that you have a farmer-first approach, and you take a lot of initiatives that are spearheaded by your own company as well as the government in the domain of organic fertilizers and also nutrients to enrich the soil carbon. So how do you envision strengthening the industry academia partnership in the domain of bioproducts that are essentially derived from biodegradables and waste, essentially for crop protection, fertilizers, and other agrochemicals?
Thank you, Professor Venu, for inviting me to the panel discussion. So Coromandel, as you know, is an agri-inputs company. And the products that we supply are, the inputs that we actually supply are for plant nutrition and for plant protection. In the area of plant nutrition, we are primarily manufacturers and marketeers of fertilizers, which includes mineral fertilizers or chemical fertilizers, organic fertilizers, specialty fertilizers. And so primarily we, when I speak about as plant nutrients, we are basically referring to mineral fertilizers. And there are two challenges that we are facing, I would say, as a company and as a nation, with regard to plant nutrition products. One challenge is the fact that all these fertilizers are based on mined raw materials or fossil fuels. So these mined raw materials are like rock phosphate, potash, sulfur. So these are all have to be mined, and there is a very high environmental impact. There's a very high environmental footprint, which which these mined minerals have. Now that is one area of concern. So definitely, as a responsible agri-input player, we need to reduce the environmental footprint of the mining activity, of the extraction activity. Secondly, and also of the processing activity, because these mined minerals also have to be processed. Now, the second challenge which we are facing is a different challenge, that India really does not have doesn't have very significant resources for plant nutrients. So we import almost 30% of our nitrogen. 70% is produced in the country. And in the beginning, we were talking about green hydrogen and green ammonia. That is one way of bridging the gap between what we produce and what we require in the country. But more importantly, 99% of our phosphorus in our country is imported. 100% of the potassium in the country is imported. Almost 100% of the sulfur that we use for producing plant nutrients is imported. Now, in the matter of zinc, which is an important micronutrient, we are self-sufficient in zinc, but entire quantity of boron is imported. So when you look at the resource availability with respect to plant nutrition, we are actually, India is not very well endowed in terms of plant nutrients. So now, but very interestingly, both these challenges of high environmental impact, high environmental footprint of mineral fertilizers, and the lack of resources in the country have one solution to it, what we see. So because the solution basically lies in the fact that, which comes from sustainability and circular economy. If you are able to have a way of recycling, reprocessing the nutrients within the country, there is a way to reduce the environmental footprint as well as to reduce our dependence on imports. So that there are two different challenges that we face, but the solution appears to be the same. The solution appears to be to rely on the concept of circular economy to recycle and to reprocess as many nutrients as we can within the country. And I'll just give you 5 examples. I have a couple of slides. I don't know whether you have. Yeah, so if you see the first slide, I don't know whether you can see it. Then there's one. If you see the first slide, one example I have is on biochar. So Professor Vinu is very well aware of this project where we are trying to convert paddy straw into biochar. Indian soils are very deficient in organic carbon. Our organic carbon is only to the extent of 0.3%, 0.2 or 0.3%. It should be at least 1%. And biochar is a way of bringing back carbon into the soil. It's also a way of reducing the carbon greenhouse gas emissions by sequestering carbon into the soil. And this is a project that we have ongoing in Punjab. And here the chemical engineering challenge, actually all the 5 projects I'm talking about are problems which require chemical engineering solutions. So the first solution I'm talking about is the design of a pyrolysis reactor for converting biomass or biomass like paddy straw into biochar in a very efficient manner, in a way which can improve efficiency and for having a technology which is scalable. So this is one example we have. It's a very live example which we are currently working on in Punjab. And India actually produces almost more than 500 million tons of biomass, which is agro waste. So this is one way of utilizing resources which are available in the country to bring back carbon into the soil. The second example that I have is a technology which is now becoming popular in the US, and that's a technology of sort of fusing organic matter with mineral matter to improve the efficiency of the mineral fertilizers. So here in the ammonium sulfate process, there's organic matter. So biomass which contains, goes through a process of hydrolysis. It is broken down into amino acids and proteins. And this organic matter then fuses with the ammonium and the sulfate ions in the fertilizer. And it becomes what is called an organo-mineral fertilizer. So rather than a mineral fertilizer, we are now talking about organo-mineral fertilizers, which are based on fusing of organic matter with the chemical compound. And this is a technology which has been implemented in Florida by a company called Anuvia. And this is something which is very relevant to the country, because if we have to improve the efficiency of our fertilizers, the nutrient efficiency of our fertilizers is very low, to the extent of 30%. We have to look at solutions like organo-mineral fertilizers. So hydrolysis is in fact going to be a very important technology for converting biomass into products which can be utilized for plant nutrition. The third example I have is conversion of sewage sludge ash into fertilizers. This is the technology which is being actually quite actively being used in Europe now to convert sewage sludge into incinerated ash, and then the ash is then converted into fertilizer to recover the phosphorus. Almost, I would say, 8 to 10% of the phosphorus which is now being used in Europe is now going to come from sewage sludge ash. And this is something which we really need to look for in this country, because in India, we don't have phosphorus. We import all our requirements. And if we are able to recycle the phosphorus from the sewage sludge ash, that will at least meet to a large extent our requirement of phosphorus within the country. And fourth, we have the technology which is phosphogypsum. And this is something which we have engaged with IIT Madras on this subject. There is a known technology to convert phosphogypsum into ammonium sulfate using carbon dioxide and ammonia. But we want to move it to a different level where the conversion takes place at the point of where the CO2 is being generated. So ideally, if you have a plant like a power plant which is generating CO2, can we have a small plant to convert CO2 into ammonium sulfate and calcium carbonate using this type of technology? And finally, I mentioned about zinc. Zinc is a very important micronutrient. In India, fertilizers don't use zinc because of the cost of zinc. And that is leading to a lot of health issues, especially for young children who are having stilted growth. Now, zinc, in fact, now can be recycled from alkaline batteries. So there is a technology from a company called TraceGrow, which is recycling zinc from alkaline batteries. And this is something very important to the country because huge number of alkaline batteries are thrown away in the country. And if we can recover that zinc from there, it can all go for fertilization. It can go as a micronutrient, which will really help our society. So these are some of the areas I would encourage institutes like IIT Madras to work on them and to develop technologies which are relevant for India and which can be scalable in India. Thank you very much.
Thank you very much, Dr. Amit Rastogi. It's also nice that you have really put up some of the promising problems to take up and those initiatives that you are taking up already with Coromandel. I have a very quick question to the first couple of panelists. So you see that the scale at which typically in academic institutes, we work on different laboratory scale experiments and what you really want to implement in the industry, there is a significant scale difference, right? So what are your thoughts on really bridging this scale? So obviously we cannot go to a scale that's as large as what you have in the industry, but we can certainly go to, something like a pilot scale, but that's also kind of limited by the typical capacities that we could process, on the longer run. So what are your thoughts on that?
I'm glad you asked this question, very interesting question. We had challenges when we moved in from lab scale to pilot scale as well. I mean, we had industry, but we still had problems. But technology for pilot plant design has evolved over a period of time, and I think it's already providing the solution. Today, we have multi-purpose pilot plants that are skid mounted. I'm sure people like engineering companies like Group and all, they do have these things. Nowadays, these can be done. They can just be assembled on site, run for a few, they're available on lease. You can run it for a long time in the industry, get your processes and the parameters set, and then you can invest on a bigger scale plant. So the bridging between pilot and industrial scale processes has undergone a massive change. And I'm sure with more things like, Industry 4.0, which can data analytics, which can real time generate the data that is needed for scale up, these things will undergo a massive, massive change. So there are no more challenges. I think if you seek to look for those solutions, you will get it. We had a effluent treatment plant. We are a zero discharge company. So we have an effluent treatment plant. We wanted to upgrade to a process where we're using spiral bound ROs, reverse osmosis process to this tube RO, and we wanted to evaluate them. So no way we want to risk a tail end effluent treatment plant to do something different from what we are doing, right? So we engaged a company which was able to give us a skid mounted 20 KLD kind of disc tube RO, a membrane set up in a container, bought mobile container mounted on a lorry. We ran the process for 6 months to establish the parameters and then invested on a DTRO. So these solutions are available today if you look for it, and I encourage even students and startup ecosystems that are available in IIT to invest in these multi-purpose pilot scale equipment that can demonstrate technologies for scale up within an industry.
Quite impressive. Thank you. We now take a shift from the industry perspective to the academic perspective. So Professor Nagarajan has been working for quite some time in the domain of process intensification. And it's very clear today that process intensification is the key to achieving sustainability in process industries, especially when it comes to improving the process efficiency or the energy efficiency and also the economics of the processes. So based on your expertise, Professor Nagarajan, So over the years, spanning a wide range of processes that you have worked at. So can you please highlight the challenges and bottlenecks for process industries to transition from, what they've been working in typical conventional processes to new processes that the process intensification routes might have to offer? And what are the best practices to essentially transition to those?
Thanks, Vinod. Well, I think the first thing we need to do is realize that processes are only used to make products. We don't ship processes, right? I mean, customers don't really care what process you use. What they care about is the products that they receive. And, humans are very aspirational. So the customers want the best possible products. And also very competitive, right? If your neighbor has a large screen TV, you want a larger screen TV. If your neighbor has a expensive car, you want a more expensive car. That's not going to change. So, when you talk about sustainability, it's not going to happen because of people making sacrifices. That's the first thing we need to realize. The existing quality of life has to be maintained, has to be sustained, and it has to be improved. So there is going to be a constant need to push improvements. We're not going to say that, we cannot use ACs anymore, or everybody has to ride on bicycles. I think that's a wrong way to even think about sustainability. Sustainability is optimizing your existing resources to make the best quality product that will satisfy the customer. So when you think about it that way, process intensification plays a major role, because you can take an existing process, and if you can make it run faster, better, cheaper, to me, that's the mantra. That's where the challenge is. If you can take an existing process and make products with a quicker turnaround, if you can make higher quality product and you can make a cheaper product, you are conserving so many resources. You're conserving energy resources, you're conserving human resources, you're conserving water resources, and you're still making a product that satisfies the customer. I think that's why process intensification is absolutely essential to sustainability without involving sacrifice. And so that's always been my view on it. And but at the same time, these improvements may not always be incremental. Sometimes you do have to think out of the box. There may be a paradigm shift that's required. For example, when I was working with IBM, I was hired into IBM back in 1988. And one of my first challenges was something I think Raghavan also worked on, which is elimination of ozone depleting chemicals. At that time, IBM's hard disk drive manufacturing facility in San Jose, California, was the largest producer of this. And they were also the largest emitter of CFCs to the atmosphere. So the US EPA was after them to do something right away. But at the same time, I don't think it required a knee-jerk reaction that says, let's reduce production. I mean, that's an easy way to meet targets. Instead, we were given the challenge of essentially redesigning the whole process. I mean, the reason CFCs are used in at least in many of these manufacturing industries is for things like solvent degreasing, removal of oily residues, surface cleaning. And so the first thing we did was see if we can redesign the whole process so that residues were not oily to begin with, so that you don't have to use solvents. So it required going back all the way to the suppliers of even screws and nuts and washers that go into a disk drive, and essentially change the process over so that all the, for example, the coolants that are used in machining, if you can substitute oil-based lubricants with water-soluble lubricants, then you can use water to do the cleaning. And that was the kind of approach we took. So it was a completely, I would say, innovation-driven approach that said, let's examine the entire process, look for opportunities to get rid of substances that require the use of CFCs subsequently. And I think we were able to not only achieve complete elimination of CFCs well before the Montreal Protocol deadline, but at the same time, we were able to increase production and maintain quality as well. So I think that's a kind of thinking that we need when you talk about process intensification and its effect on sustainability. Another example I can think of is, again, in agricultural technology, there is a push now to go towards nano fertilizers, nano nutrients. I think that's, again, a very smart move because it ensures sustainability, because it minimizes use of resources. while at the same time delivering even higher productivity so the farmer can get more out of their land than they're currently achieving. So it's again a win-win. So I think any sustainability solution, if it involves process intensification, it becomes a win-win solution. And that's, I think, what we should be driving towards.
Thank you, Rajan. That was indeed a very response. And let's continue on this process intensification subject with one more view from Mr. Mahesh Bagle. Mr. Mahesh, talking about process intensification, one of the green ways to achieve sustainable production of chemicals, fuels, and today bioproducts is to use what we call as supercritical fluids as solvents. And the use of supercritical CO2 or essentially CO2, which is one of the major, we talk about achieving net zero today. And one of the pathways could be to actually use CO2 in various applications like separations to reactions and so on. And you've been working exactly in that domain to use supercritical CO2 to extract or kind of deconstruct the biomass in the domain of what we call as second generation bioethanol. So we'll be happy to hear from you and your thoughts on that.
Of late, everybody is talking about green technologies, green fuel, green hydrogen, green. And the world is slowly realizing, when we talked about chemical industry 200 years back, chloralkali, a lot of things have come, fertilizer industry. And over the years, we realized that what our world was 200 years back or 300 years back, not the world today. We do have a lot of molecules which were not in existence. When one of the clear example would be a chlorine. Chlorine was stabilized multi-years back. We sort of opened that up and led to a lot of sales. So today, everybody is talking about green. And one of our efforts is, we are not a chemical company or anything, but by chance we got into technologies. There's a discovery, which happened quite a few years back about the CO2 and supercritical state of CO2. What it does is, in a supercritical state, CO2 is an extremely powerful solvent. So therefore, it could replace a lot of the solvent processes in a sustainable way because CO2 is available for free. And it doesn't really sort of create a pollution, what we consider as a pollution, although there is a global warming which is happening. So the technology currently we are sort of, we just investigated something and which we are partnering with IIT on this. It's called as supercritical explosion. Just to give you a roadmap into this is there are some charts here. We have a huge, let's say, availability of lignocellulosic biomass. And a lot of processes are being evaluated, say pyrolysis. But one of the routes, this particular mass also contains starch. And that starch is covered by one of the toughest, let's say, unimer, which is lignin. And almost everything which everybody is talking about, how to get rid of this, I'll use some mechanical attrition, I'll use some chemical processes to get access to my starch molecule. And therefore, the word 2G came about. It was very easy to sort of ferment something which is molasses or sugar, fermentable sugars, but how do I access this starch molecule, which is so abundantly available otherwise? And out of, let's say, in a 2G technology, mechanical, chemical processing, the third one, which is currently being explored at a lab level and which we want to take it to a sort of next level, is supercritical explosion. What it does is, if I take this supercritical CO2 at a very high pressure and subject my biomass, or lignocellulose biomass, for as low as 15 minutes. And then I let that explode. Explode in the sense I release the pressure catastrophic. Now that's where the engineering challenge comes. But if I can do this, then there are lab experiments which are probably done at a small capillary tube level, which exposes almost to the extent of 85 to 92% of starch molecule available for you for the further. Now the challenges in this are multiple. I mean, we are part of we are our own internal, let's say R&D. We are partnering with IIT because we are finally a company which is driven for profit. And this particular technology, we believe will have a good potential, primarily because there is no downstream negative. We don't have, it doesn't create pollution, it doesn't create, at least this part. So the challenges in this particular area are, number one, supercritical CO2 is a very, very powerful solvent, which means it attacks almost anything. So to create pumping systems, create valves, create vessels with seals, itself has been a challenge. And over the last maybe 10, 12 years, cybernetic has been in this field. We have developed this right from the scratch. I mean, right from the first principles, pumps are designed, primarily because these are sort of compressible fluids. Your pumping efficiency can be as low as 10% if you don't design it right. Then comes the so-called explosion. Now, as you know, there is a sudden pressure drop. You have a Joule-Thomson effect. There's a lot of freezing. I mean, if anybody has handled CO2, you know how difficult it is to handle CO2 in a supercritical state. So this is something, a valve, which we feel we are designing, and it has to basically function as a rapid decompression. And this is something what we want to do. I mean, we do build pilot plants for all this process because one of the other application of supercritical is a lot of extraction. So the extraction, I mean, current flavor is cannabis because it's for medical application. But cannabis, actually, cybernetic is a leading company in this area. But this, for us, is a sideline in the sense this can lead to a lot of global if we get it right. And so there's a research and which we are sort of trying to work.
Thank you. Thank you, sir. Again, as we have seen the flow of discussion, we kind of started from, with Mr. Venkatraghavan talking about, the water to Ramit Rastogi talking about the biochar and the use of various enriching the nutrients of the soil to process intensification to CO2. And let's continue with CO2 for some more time with Swapna. Swapna, the management of CO2 emissions is one of the crucial aspects, and I'm sure you're dealing with a lot of projects, both fundamental as well as applied in this domain of CO2 sequestration. There are standard processes based on CO2 absorption using amines. So what is your take on some of these processes that the industry is currently adopting, and what do you think is a way forward for maximal recovery of CO2 to achieve the net zero goals?
Hello. Thank you, Venu, for inviting me for this panel. It's my honor here next to all the experienced people, and I'm very honored to be here. And yeah, coming to the CO2 capture and sequestration problem, the management of the main challenge for CO2 capture and for sequestration is the cost of this technology. So there are technology available, like a well-developed technology, for example, as you mentioned, amine-based or like a sorbent-based, which is, and also some new technology are developing, but the main challenges come in the cost. For example, if you talk about CO2 capture, it's not only the capture technology, it will also include the capture, transportation, and the sequestration. So altogether, it's how much is the cost. So if you see in the global, I will give you just to give you a status, like, I just checked like in International Energy, Energy Agency's report, where you said only 300, only 30 CO2 CCUS unit is now ongoing, and which is capturing around 42 megatons per annum. So which is around 0.1% of global CO2 emission, which is very low. So if you wanted to achieve the target of net zero by 2050, you have to build around 2000 units. So we are lacking behind, like all the world in terms of CCUS activities. The main challenge is again the cost. But again, how to solve this cost? As you said, like the R&D is, there are a lot of research is working on in different technologies as capture, which is a mine-based, a new solvent material, new sorbent or new. For example, one of the main aspect is to space also. Apart from the cost is also space. You need a space for the carbon capture unit. So how to build the compact reactors? Those are the R&D, basic R&D, which is going on. And another important point is I wanted to mention about that the CCUS unit going forward from capture to the storage. So there is also a U, right? Utilization. I think in this panel, there are very interesting utilization of CO2 is mentioned, for example, supercritical CO2, and also it can use for the fertilizer. So CCUS is an important aspect or important way to go forward, but again, we have to see the revenue. For example, what is the market price of the utilized product, of the value-added product? Is it giving you a revenue, how much is the profit? So a lot of economic aspect is involved. And storage is one, again, CO2 storage, where CO2 is captured and stored in the subsurfaces, which is again a very mature technology. It was already commercialized in Norway and US. But again, in that case also, there is no return of money, right? You capture the CO2 with a lot of money and then you just stored. So there is no revenue. So those aspects, that's why this cost parameter is very, the most important challenge for CO2. So if you say what is the way forward or sustainability, one is to convert the a CO2 switch, the converting all these energy sources into green energy. But again, green energy is inevitable, but you cannot get the green energy on the next day. You have to wait for it. It takes a lot of time. It will, before you your energy demand fully depend on the green energy. So you have to, we are still will depend on the fossil fuel energy for quite a long time. So we have to depend on the CCUS, So according to me, one going forward is to combine CCUS and CCUS. For example, you cannot utilize all the CO2 which is generated, which is around 40 billion tons per year, according to the IEA report. So we cannot utilize all the carbon dioxide. So some may be combination of utilization and storage, maybe a recent or immediate solution. But yeah, in the future, we have to look for green energy resources or new alternative energy sources for this net zero. So that's why I
think that was a very clear response in terms of the cost that you highlighted is the key to drive this change. So with all this discussion, I would now like to have Mr. Prasanna Kumar, who is actually heading the sustainability initiatives at Tube Investments of India. So Mr. Prasanna, you are heading the ESG, what we call as environmental, social, and governance framework. And even Mr. Venkatraghavan spoke about it in his response. It's becoming an integral part of industries and businesses. And being the head, I think you are the best person to really highlight and also enlighten us on the specific implementation strategies that various companies are adopting. And more than a corporate compliance or a financial performance indicator, right? So how do you see ESG is really kind of percolating down to the consumers, the products, right? And for the society at large.
Hi, good afternoon, everybody. Thanks for inviting me. I think that's a 20-mark question that he asked me. So I have to give a proper response. Last time I sat amongst a bunch of doctors who was at Apollo during COVID. Makes me very humble here. I'm not a chemical engineer, so will not be getting into any formula or anything. I'm a manufacturing person. I've been trained to make production happen. I worked on a bunch of new business startups. So ESG is something new for me as well. And I was working on we're launching a new business at TI, and then this thing came up. It's a government mandated, SEBI mandated initiative, ESG. And so we did not have this before that mandate. So I'm also learning a lot of things in this. So when I look back to understand sustainability, first, when you step back and see where this planet is spinning in the dark space and how far away from the sun, it's got a small bandwidth, right? If it gets a little closer, you cannot live here. If it gets a little far out, you cannot live here. So it has this little band. So as engineers, what we do is we have to set limits for any process. In science, they come up with the theory and they'll prove or disprove it. In engineering, you have to make it, actualize it, and you have to set limits. So even human body, like 98.6, if it goes up 0.2 degrees, you have a fever. Clinically, they will say you don't have a fever, but you can feel it. So it's then the whole thing about sustainability is what did we get, and what are we having, and what are we going to leave behind? So I zoom out and look at things. Growing up, I could get water from the well and drink. Today, if you go to Ambattur and get water from the bore well, it'll be yellow in color. You drink it, good luck, get a good insurance plan. So, ESG is actually the Panchabhutams. We like it when the white man comes and tells us we have to do ESG. But when your grandparents told you to follow the Panchabhutams, we will question them, right? So what is it? Earth, fire, air, water, space. We'll go one at a time. A general comment, and then what we do at TI. Earth, a beautiful planet, 71% water. Thank God it's 71% water. 29% land, of which only 10 or 12% is habited by humans. That's a good thing. We cannot do more damage than that for now. So we have not occupied a lot of this planet. But wherever we have occupied, we have created a little bit of a mess. So I grew up in Trichy. In Trichy, there is this Rockford temple, a big rock. Well, it's as old as this planet. During the day, you can step on the rock. It won't be hot. But once the sun sets, ambient temperature changes, the rock will start releasing the heat. And you can't step on that. If you live near there, you cannot sleep at night. Some interesting things. I used to stand there and observe it. Today, I'm actually utilizing it for something else in furnaces. So Earth, what do we do in TI? We look at wastes, hazardous and non-hazardous. And then we have to separate them into how you process it. You incinerate it, you recycle it and reuse, or you bury them, landfills. So the mandate is we have goals for each of them. And we have 5 years worth of data. It was incredibly challenging for a legacy company to go get data. We are actually very good with data. We have a lot of information, but transferring that into information that you can utilize has been a challenge, but we have it figured out. So now we have mandates to reduce the landfill, recycle and reuse a lot. Reduce waste. Once you realize how much waste is actually being produced, it doesn't come in the P&L. only look at top line and bottom line. This one is a big line item actually, waste generation. It gives you you step back and think, oh my God. The second one, fire, energy. Energy, you have electricity, and you have oils that produce energy or gases. So we have renewable energy, we have grid power, and then we have a mandate to go to increase our renewable energy content. So we are working on it. Those things are always regulated by the government. And then oils. So we have furnaces that use natural gas or propane, or sometimes we also have electricity operated furnaces. It's very difficult to replace them. We don't have technologies to not use those gases, at least, without blowing them up. Look at it in your own houses. You all have LPG gas stove. You want to do good for the planet, switch it off, don't use it. Try something else, solar cooker. That marriage will fall apart very quickly. So it's not easy to replace some of these hydrocarbons. In fact, the West has developed their society on the back of hydrocarbons. This is my personal opinion. I think the awareness is good, but when you see a huge population in Asia, China and India growing, I think there was a need to put some checks and balances. So that was fire, right? Earth, fire, then water. So if you're a Chennai person, I remember in the 80s, you can go buy those plastic kodam. This is when NGR was the chief minister. We had water crisis even then. And bore wells used to go down over 100 feet. So that's not new. But we can do better. Like I said in Ambattur, the bore well water is not clean water. So what is the responsibility of an organization? A large organization, like the SEBI actually has said, the top 1,000 companies has to be compliant with ESG, and it has to be a part of the annual report. So it's called the Business Responsibility and Sustainability Report, BRSR. So it's good that it is getting mandated. But at the process level, what is required is zero discharge. We're just talking about it. We are working on it. Many of our factories have it, some don't. We are working on it. You cannot spill water outside of, any water into the ground. So water is used in bathrooms. It goes to STP, gets processed, it's used in gardening. Water used in processes goes to ETP. And the goal is to use more of it back in the process. Whatever that doesn't get used back in the process needs to be discarded without sending into the ground. So we have to evaporate it. So a lot of mechanical evaporators are being purchased. So we can become a zero liquid discharge company. It's a mandate. So earth, fire, water, air and space. See, when it comes to air quality, there is pollution. If you can see smog, that is not CO2. Okay. Just because you cannot see the Taj Mahal doesn't mean there is greenhouse gases everywhere. You cannot see them. That's pollution. So we have NOx, SOx, we have stacks that we need to make sure they are below a certain limit, and we need to work on scrubbing them constantly to make it better. That's the mandate there. But then we'll go to greenhouse gases quickly. Greenhouse gases, well, if you go look at it online, does anybody know what the largest greenhouse gas is? It's actually water vapor. 96% of greenhouse gas is water vapor. CO2 is actually 3.6%. What's the percentage of CO2 in the air? 0.04%, of which 3.2% is man-made. So these are all real numbers. We have to leave a cleaner planet for the next generation. We cannot pollute the land, we cannot pollute the air. We owe it to ourselves, our health, and the children and grandchildren that are yet to be born. So it's important that my managing director looks at this as do the right thing for this planet. And it's nice to hear it from him. There is a commercial side. We are here to make profit, like what he said. But we need to step back and grow in a responsible way as a company, as a society. And also in TI, we are a cycle company, right? Once upon a time, we made bicycles. So we are actually a earth-friendly company when we started. Now we are again getting into EV under the brand name called Mantra. It's interesting how that will go. But I'm also hoping for sustainable energy long-term. You can't buy oil from one country and lose foreign exchange and then go buy lithium from another country and lose foreign exchange again. A good sustainable solution would be good. I'm really hoping that I saw some hydrogen names here and there. Hopefully in the next few years, some new startups will take off and make it commercial, make it happen. We can actually lead this. You know, I think Parag was saying that sitting in India, we are close to the equator. We have copious sunshine, wind. It's a great place. So I just remembered, you know, just thinking about this beach. You all see the news about the Pumbuhar city that was discovered just a month ago. Google it and see it. It's a 250 square kilometer city off the coast of Nagapattinam, sitting 50 to 100 meters below the sea level. The river Kaveri runs 40 kilometers into the ocean. I think if you stand on the beach and the farthest you can see is, I think, 10 or 12 kilometers. You know, I may be right or wrong, I don't know. But 40 kilometers into the ocean, Kaveri is running. So they are able to see it. So why did Pumbuhar go into the ground? We don't know. But the Chola kingdom was using that as a port city. Why is Dwarka inside water, underwater? We don't know. So the earth always changes. Climate changes all the time. There is not a point in history when climate never changed. But we want it to change in a way where we can sustain life. We don't add to the already complex systems. I used to have one more comment. I used to sit and watch National Geographic all the time, documentaries. So one of the fascinating things I saw was they discovered the skeletal remains of a blue whale in the Sahara Desert. That just blew my mind. I mean, how the hell is that possible? Skeletal remains of a whale in the Sahara Desert. And then my favorite one, Greenland. It's sitting between 60 degrees and 77 degrees latitude. The place is called Greenland. You fly over it, you will see sheets and sheets of ice. Why is it called Greenland? Well, it turns out they were farming there. The Vikings were farming there. And herbivorous animals were roaming there. This came out in National Geographic in the first week of December last year. So herbivorous animals were roaming around in Greenland. Why do we have what we have there today? I don't know. Good at asking questions, don't have answers. So let's be responsible as citizens of this planet. And we need to do whatever we do, we need to have a sustainable way of looking at things. Very important. Do pranayama. you will not release CO2. A little bit, it'll help your health. Every person releases about 1 kilogram of CO2 per day. 6 billion people or more. Think about that also. Anyway, thanks for the opportunity. Great ambience, enjoyed it. A lot of things I'm soaking up. Hope to be around here for a while. Thanks again.
Thank you. Let's open up the session for a few quick questions from the students or from the industry participants or from the faculty of the department. To any of the panel members. Yes, sir.
First of all, thanks a lot. It is an insightful session. I'm representing Ultramarine Pigments Limited. So the question is about scale up. Scale up is always very important, right from lab scale to pilot scale, and then pilot scale to the main plant. So it becomes very simple when we have main plants where we want to take trials in terms of process intensification or in terms of product change. So we can establish in pilot scale and then we can directly move on to the main plant trials. So it becomes very simple because we have the hardware. So in case if you don't have the hardware, we are only with the pilot scale level, then how are we going to scale up it to the main plant? So maybe some complex processes are involved. So we don't have, we may not have any direct ideas to go for a main plant trials. In that case, maybe we can leverage CFD. That could be one tool where we can use it for scaling up. So I would like to understand from the industry experts, like in your past experience, whether you have leveraged the CFD when it comes to scale up from pilot level to the main plant. So that is what I want to understand. Thanks a lot.
Yes, Mr. Mahesh.
So broadly, when you talk of pilot plant and scale up, usually the basis is at the lab level. Lab level is where you set up your process. That means I know what my input is and I know the quality of output. The next stage, before going to a big leap, you need to figure out what is your energy balance, what is your mass balance. Because these two things alone will answer a lot of your questions for the big. So a pilot plant usually is scaled to that level where these answers are sort of repeatable and you are able to sort of quantify what is my energy cost and what is my mass balance. So normally industry, I mean, because you have multiple processes in this. So there are certain risks because finally, if I want to scale up something, you say that computational fluid dynamics I need to use. Is that the word you're asking? Yeah. So broadly, what happens is these are the areas where you use these tools when the risks are very high. For example, let's say I'm designing a furnace for say 3000 degrees centigrade. And there is certain amount of, let's say, heat transfer which is expected from part A to part B or whatever. Now, these are the things which you cannot simply risk it, even at a pilot level. So normally that's the time you use, let's say, CFD for analyzing every year. I mean, I'll give you an example. We were designing a continuous calciner, which was almost something like 70 meters in length and going through multiple stages, right from 200 degrees up to 700 degrees, coming down to, let's say, cooling point. And what we realized is, I mean, what we think as a common sense engineering, you have a fan circulating hot air, I mean, medium and everything. You can generate hotspots. And at that hotspot, at 600, 700 degrees, you definitely risk a meltdown. So this is where CFD genuinely helps. And we use that. Of course, you don't use it for every application because it's an expensive process. And it also then is scaled up to actually modeling. I mean, what we do is when we do this particular array, I have arrived at, let's say, one module. I actually build one. Put it through a sustainable process of, say, 72 hours run, go through all the processes, monitor every temperature. Make sure my fans, which are probably running red hot, at that point, they all work. And that's when we say, okay, we conclude we are taking a risk. Believe me, this kind of calciners cost more than 10, 12 crores, piece. And you definitely can't risk it. So, I mean, that's the usual process.
Maybe I'll also respond briefly to your question. So in the fertilizer industry, like we have a pilot plant. We have set it up in 2007 at the cost of 5 crores. It's a 1 ton per hour pilot plant, which mimics our actual plant. And our plants typically run at 100 tons per hour. So the scale up factor is about 100. But we are very confident that whatever results we get at 1 ton per hour are fully scalable. So it depends also on your scale up factor. Is it 1 to 1000 or 1 to 100? So what scale up factor are you looking at? Coming to your second part of your question on CFD, we have used computational fluid dynamics. We have used like software like Fluent to model equipment, but we don't depend entirely on it to design a plant. So, let's say we have used CFD to model a sulfuric acid reactor, a converter, which is modeled as a catalytic bed reactor, fixed bed reactor, to look at what will be the conversion efficiency. So we have used it to model ducts, airflow in ducts. But to design a complete plant, because it answers only some part of the engineering challenges which you face while designing a plant. Not all the engineering questions can be answered by CFD.
Thank you. Batch.
How easy it is manufacture carbon dioxide system? Why am I looking for single
Crystal.
So thank you for your question. So you are asking about CO2 in terms of, for example, for concrete materials to CO2 crystals. Yes, yes. Okay, good to know about the one of the utilization process of CO2, which can be used as a, for example, as a crystal material. So I would say it will be again, one of the CO2 utilization process is CO2 into the concrete used as a concrete material, which is commonly used as a mineralization process for one of the usage of CO2. Another usage you mentioned, it can be used as a surface roofing material in types of, it's very interesting. And I'm sure, I don't know what will be the cost of that process to make the crystal, but I'm sure it will be a very, because solid is transforming into a solid, the CO2 is gases transforming into a solid form. So there will be a different processes. I'm sure there will be a cost involved into it, a very high cost, but I don't know the exact price of that technology.
Thank you. Very good questions and very useful discussion. So we come to the end of this session. I don't want to be, delaying for the next session on energy and carbon neutrality. So thank you very much to all the panelists of this session. Thanks for adhering to the time. We were slightly delayed, but I think it is worth it for the discussions we had. So let me now invite Professor Kannan of Chemical Engineering Department to hand over the mementos to all our panelists. Venkat Raghavan. Mr. Mahesh Wagle. Mr. Nagarajan. Mr. Prasanna. Mr. Swapna. And Dr. Amit Rastogi. Thank you all. Thanks for the nice discussions. Let's await the next panel discussion that will be chaired by Rajneesh.
While we are waiting for the next panel, also would like you to point that there is an IP cell stall there, which has details of all the patents from our department. Whenever you have a chance, please take a look at it for further discussions. Thank you.
Good afternoon, everyone. The next session is on energy transition and carbon neutral solutions. So we would like to invite the panelists on guys over here. One of the panelists, Mr. Ravi Kumar, is joining online. He's from BPCL. So he is going to be online through Zoom. Other panelist, V. Murthy, I request him to please join us. Mr. Parag Sepe, please come over. Professor Priti Agalyam, please join. And Arvind, Professor Arvind, where is Arvind? Hey, Arvind. I'm not allowing you to have water. You can here. Sorry. Okay. And Professor Himanshu, I see him here. Yeah. Please. No. Okay, so I don't want to waste any more time because I know that after this we have lunch and all of you would be hungry by that time. So I like to finish it off before 1. I will start with a quick introduction. I'm not going to go into too much of detail. So the first speaker of today is Mr. Ravi Kumar. He's a senior manager of BPCL. He was previously associated with EIL, Engineers India Limited, and he has a BTech degree from Andhra University. The second invited speaker is Mr. Murthy. He is a senior principal engineer, product technologies. He was previously with Dr. Reddy's, Dow, GE, IOCL, so many other organizations. And he is our alumni, and he is also an alumnus of XLRI Jamshedpur. And today is our chief guest, and one of the panelists in this group is Mr. Parag Sepe. He is Chief Engineering Officer and Executive Director Engineering at ThyssenKrupp, and he is an alumnus of LIT Nagpur, and he has done his MS from Hamburg, Germany. The other three, Professor Arvind is our faculty, Agalyam is also our faculty, and Himanshu is also our faculty, including me in the Department of Chemical Engineering. So let me see if we can invite Ravi. He is already there. Yeah, Ravi, can you hear us?
Yeah, I can hear.
We are not able to hear you, Ravi, for some reason.
I can hear you. Am I audible?
Sir, you're audible to me. I think it should be the same with the terrace also, the hall where the event is happening.
I'm able to hear you.
Yeah,
Yes, sir.
perfect.
Just a moment, sir. I'll
can
speak to the terrace hall and get back to you.
Okay, thank you.
Okay, Ravi. So I would like you to start the discussion. We would like to understand the current energy mix in BPCL. What do you see is the future of the energy mix in our country, and how BPCL is basically trying to look into this energy mix and trying to overcome all the challenges we are going to face on oil and gas industry because of this clean energy push which we have seen in recent past. Please, Ravi.
Yeah. Okay. First of all, thanks for inviting me, and many thanks to Professor Pushpavarnam and the entire team of Chains. So as per the international reports and also our thought process here, most of almost 80% of the energy mix is fuel based. Okay, and as far as BPCL is concerned, refineries contributes more than 95 to 98% of the energy use, and whereas the rest is for marketing and other locations, and most of the usage is based on fuel oil and to some extent gas. So basically what we are thinking is, when we try to switch to net zero much before 2070 as a country as a whole, we have set a target of reaching net zero with respect to scope 1 and scope 2 emissions. Scope 1 is basically our own internal use for our running the refineries and other basically facilities. And also scope 2 is about steam, electricity, etc. So with respect to these two CO2 emissions, we wanted to be net zero and basically no emissions by 2040. For this purpose, we are basically looking at 4 key aspects. That is increased renewable energy usage. And for this, already we have set up a lot of electrolyzers, and also solar energy we are going very, very aggressively. And we have set up a lot of several megawatt scale solar plants. And then improving the energy efficiency. As you all know, refining is basically distillation based process, and it's the most energy consuming process. And also we use a lot of hydrogen. These two basically result in heavy energy usage. So first of all, we have to target fuel oil consumption by replacing with renewable energy like compressed biogas or natural gas to some extent. And the other one is to use solar based hydrogen, green hydrogen production for refining, so that you consume less amount of energy. And also the other point is about improving the energy efficiency of the refineries. And when we want to switch towards net zero with respect to scope 1 and scope 2, majority of our product portfolio has to shift towards chemicals and with the carbon capture, and whatever fuels that were going to be produced, they need to be basically produced with least amount or zero amount of carbon dioxide. And for this purpose, we employ renewable fuels and also shift towards petrochemicals, so that we have to remain in carbon business, but at the same time, we focus on value-added items, because we cannot just like that move from crude refining industry to something else. But in this transition, we also look for opportunities that are going to add value, especially for energy storage. So our motto is to become a energy company rather than only a crude oil based company. So our slogan is basically energizing lives. So in line with this thought process, what we are planning to do is to switch over to storage systems and green hydrogen. For this purpose, we are collaborating with premier institute like Baba Atomic Research Center. So as you all know, the electricity and the green hydrogen production are going to have huge demand in future, and BPCL also needs a lot of green hydrogen. And for this purpose, we need electrolyzers. We already in the process of setting up 20 megawatt scale electrolyzer in one of our refineries. For this, we are investing huge amount of money. And when you indigenize these technologies, you are likely to save huge amount of money. So therefore, what we are planning to do is basically, so indigenize the existing capabilities and scale up to the larger extent. And the second point is bio-CNG. So how do you produce bio-CNG? So already the CNG basically natural gas and methane production, methane usage is going to go up as a transition fuel. And especially when you use biofuel like bio-CNG, so it is a renewable. So from that angle, we already collaborated with IIT Hyderabad, and we are going to set up our plants based on their technology, and jointly we are working with them. Similarly, we are also working on carbon capture technologies based on process intensification based routes. So we are working with one of the premier faculty who has got a lot of experience in this process intensification area. And we already established a high-G deaerator for producing boiler feed water with almost nil oxygen content, parts per billion level. So it is purely based on only simple nitrogen and high-G based technology without much steam usage. This also is going to save a lot of energy. Like that, we are trying to use these high-G based technologies more aggressively. And as I told you, the key focus is basically biofuels, shifting from fuels to chemicals, and usage of natural gas, and aggressive use of renewables and renewable energy. And also we are setting up a lot of e-mobility centers, basically for charging and battery swapping technologies, etc. So I would like to highlight a couple of points here. So we have come up with energy efficient LPG stove. Typically, the domestic LPG stove gives an efficiency of around 68%, that whatever we are using in the our kitchens. So we have come up with an innovative design that is improving the efficiency from 68 to 74 plus %. That means almost 6-7% more efficient it is. And if you replace this energy efficient stove with the currently available stove in the market, we already patented this and sold more than 50,000 stoves already in the market. And soon we are going to launch this product through Amazon portal also. So once we start using this, there is a huge amount of energy saving potential. Similarly, so in the city gas distribution also, people are using CNG, PNG based burners. Here also the efficiency is around 60-62%, whereas we have touched close to 70% efficiency. So that much almost 6 to 7% more efficient PNG burners also we develop, and these also we are going to soon launch to the market. So they have got a lot of potential. So as far as hard to abate sectors are concerned, so since some replace the fossil fuels, there you need to have some amount of like diesel type of fuel. So we have already know-how developed for utilizing carbon monoxide and hydrogen and convert into diesel-like fuels, like using Fischer-Tropsch synthesis, etc. Similarly, we collaborated with Australians for producing dimethyl ether, which is a diesel substitute. Again, this particular material also can be produced either from methanol, or you can also produce directly from carbon monoxide and hydrogen. So carbon monoxide and hydrogen can be generated based by electrolysis of carbon dioxide and water. So once you have this technology, you can produce these synthetic fuels. So as far as energy efficiency is concerned, so we have got several initiatives using especially some digital tools. So we have come up with a new product called BP Mark. It's based on 3-4 properties. It predicts the entire crude assay within few minutes. So the advantage of this particular tool is you can go for online optimization of crude distillation unit. Typically, crude distillation unit consumes almost 4% of the energy. So if you can save at least by 0.2, 0.3% energy as 10 to 20% of the energy use using this online tool, so you can save a lot of carbon emissions. So this particular product is also has been launched, and we have already signed an agreement with Aspen Tech, and soon we are going to have a big program along with them to market this jointly along with Aspen Tech. And we also work with Engineers India Limited to develop a technology for divided wall columns. So, and as you know, divided wall column technology is much better than having a simple distillation process, especially when you are separating a product into feed into 3 or more products. So for this purpose, we have already demonstrated this technology and replacing several columns using this divided wall column technology. So similarly, I told you this High-G technology and also one crude compatibility model also we have developed. So especially this is very, very useful. So to predict whether when you mix two crudes, any precipitation is going to happen, or whether they are compatible or not compatible. So without doing any experiments, based on few physical properties, within no time, you can predict in which range they are compatible and which range they are not compatible. So this is also very, very useful, especially in a oil scenario where the demand for different crudes and opportunity crudes is very high. That time you can quickly identify which all crudes are compatible and which can be processed very easily. So these are some of the initiatives that we have been taking, and we would like to closely work with academic institutes, especially for developing tools that are especially for energy storage based on pet coke, etc. So once you calcine pet coke, you can produce the materials that can be used for efficient energy use. And so this energy storage is one of the prime focus areas, and we would like to work in this particular area, and also green hydrogen and energy efficiency improvement programs. So these are the 3-4 areas we would like to focus more in the coming years. And also, of course, the synthetic fuels is also one of the key areas where you have hard to abate sectors. So based on the technologies that have been developed, especially when you want to valorize the standard natural gas, etc., instead of flaring, you can set up a small facility where you can convert these standard gases into liquid fuels, and especially in companies like ONGC and upstream, where you are going to flare a lot of gas that can be easily converted into liquid fuels using these microchannel based technologies, etc. And also we would like to pursue these process intensification. These are some of the areas that we wanted to work closely with academic institutes. And thank you.
Thank you, Ravi Kumar. It was really exhaustive list, and I understand that BPCL is not going to leave carbon business, but they are going to diversify into many other areas, including hydrogen, batteries, solar, and others. So my next question is for Mr. Murthy. What basically Ravi Kumar talked about was converting CO2 and decarbonizing the industry and converting CO2 into value-added chemicals and especially this diesel substitute and synthetic fuels he talked about. Why personally, what I feel is that the biggest challenge in this CO2 utilization is the CO2 capture step. We currently produce roughly 2.9 gigatons of CO2 every year in India. And the gas which comes out is roughly 29 gigatons because only 10% of this is CO2. So you will have to basically process such a large amount of gas by some material which you have to use to capture the CO2. So I see the biggest challenge right now is the capture of the CO2 because unless you capture the CO2, you're not going to utilize the CO2 because most of the processes which are talking about utilization of CO2, and I guess there was some talk about CO2 crystal, it will only be feasible once you have captured the CO2 and made a pure CO2 out of impure CO2, which we typically get from all the stacks. So I would like from you to explain us what challenges you see in Shell. And I'm aware that Shell is in really advanced stages and they're also producing huge amount of liquid fuels out of CO2. So could you please talk about what kind of research exposure you have had in past and in what Shell is planning to do in next 10, 15 years in this particular domain? Okay, I had a couple of pages to be presented and really project those pages. Helpful. Hope you are able to hear me. Maybe I'm checking at that corner. Can you guys hear me? Maybe I'll start with my initial impressions here as I moved into this panel discussion yesterday. So I thought actually I'm really going to join a students event. That was my impression as I walked into this place. Then to me, then it almost appeared like an energy transition summit. So I was just walking through all the posters there. And then essentially you're covering most of the facets of energy transition. I see on the extreme left side, capabilities that are needed for energy transition. Then I see quite a bit of information on hydrogen and then waste handling, pyrolysis, and then recycle the other element, what I see. So it's so impressive that you are already leading energy transition in some sense. So I really want to appreciate or recognize the leadership that's really coming from this institute and the faculty in essentially shifting the portfolio more from capabilities into real applications that are relevant to this country and also the globe overall. So I really want to appreciate both students and faculty. Well, actually, I've been asked to talk a bit about the energy transition related topic. And also Rajneesh mentioned about CO2 and how we are really going to utilize CO2 and make it a viable feedstock. But what I quickly realized is that that's always the risk you have when you get into a meeting and start talking a little later. And the previous speakers should have already covered a few things. I thought Professor Sapna, right? She gave quite a bit of overview on CO2 capture, utilizations or sequestration, and the key issue of processing and associated costs. And I think they're really going to stay for some time. So what I'm really going to talk about is more about nature's way of sequestering carbon and how could we really leverage that opportunity is what I have a couple of pages to quickly run through. What I'm also going to do is not a big overview, rather I simply focus on one topic so that you have an opportunity to assimilate and also ask you questions, because really looking for some fresh thinking and fresh blood into all the activities in energy transition. As being very conventional chemical engineers working for the last 35 years, sometimes I feel we are
we say everyone to be out of box, but we tend to be inside the box. Yeah. You apply the same yardsticks of economics, you apply the same yardsticks of process efficiencies, then any new idea is really going to fall off. Yeah. So that's where we really want to, personally, I want to hear from all the faculty and you. So I think the previous speakers and Ravi Kumar gave a pretty good overview on the energy transition. I would really like to go to I would skip the first one and go to the second one. And you must be seeing a energy transition scenario from the next one, please. Yeah, so can you guys see the energy transition that's really being projected by International Energy Agency? You are able to see that, right? So what I really wanted to highlight here is that we are trying to move towards net zero situation where our CO2 production or CO2 that is being generated by all the human activities, we really want to get it to zero. So if you look at this chart, what you see is, like Ravi just mentioned a few minutes back, the energy mix, if we see today how it is, about 80%. Yeah, echo is good. They're essentially reiterating what I'm saying. That's fantastic. Yeah, thank you. So that is 80% is fossil, primarily by coal, and then you have crude, and also some amount of natural gas being actually used as a source of energy. But if you look at what's really happening as you really move towards net zero, the percentage of fossil fuels and fossil feedstock comes down to somewhere between 5 to 10%. That's what you see here. Our overall energy system still remains around 600 say, exajoules. It's a big number. Yeah. You still remain there. That number is really not going to go up, but our energy mix is really going to change substantially. It's bulk of it is renewable. Maybe it's wind energy, or maybe it is electrolyzers based on green energy, etc. But the contribution of natural gas, oil, and coal comes down substantially. So the question then we need to ask is that, no, if you really look at the fossil fuel consumption as of today, we consume around 100 million barrels of crude oil a day. And out of it, about 11%, which is say 11 million barrels a day, goes into chemicals, materials, and a lot of differentiated products, which are really essential for human life. So the question we need to ask is that as we really move away from all the fossil systems, fossil materials, what's really going to be our carbon source? We still want to make the products, materials, and chemicals which we are currently making. There is no carbon available. Yeah? And can we say we don't need these materials? The answer is no, because if you look at human development, chemicals and plastics have made enormous enhancements to human life and human development. Imagine a car bumper, which was, say, 40 years back. We were actually putting steel car bumpers. And today, we have replaced it with polypropylene, which has much lower carbon intensity. Yeah, and that's the case with a lot of plastic applications. Look at buildings and construction. You replaced many parts from steel and other metal into plastics and polymers, and they reduce carbon footprint enormously. So as chemical engineers sitting here, we need to really recognize that plastics, polymers, chemicals are going to be, are going to be essential ingredients for human life and human development. And we can't just go away from them. You could always say the problem is more with the way we handle them. It's not per se with the materials as such. and the functionality what they deliver. So I want to really tell this because some people say oh, plastics are bad. That's really not true. Yeah? So if we still want to make the same energy solutions, and if we still want to make chemicals, polymers, and materials, where do we really get the carbon from? So that was my question. And I did really see quite a number of answers there. Yeah. So I'm not really going to ask that question. I thought that would be a riddle. I would really ask that question to you, but you already know. So if you can really go to the next slide, which is really going to be my last slide. It kind of talks about the emerging, there are multiple actually animation. You can just click multiple times. The entire slide is really going to be open. Yeah. So if you really look at future energy and chemicals hubs, then if you really ask, what are really going to be my feedstock? And you could also ask, what is the India connection there? That's really important. And then, what is that I'm really going to do to really move forward in energy transition? I think there are going to be a few key perspectives. So as you really move away from fossil fuel, biomass is really going to be playing a key role. And I think that's a unique value proposition for India because as I think Mr. Rastogi mentioned, yeah, we produce around 500 million tons per annum of agricultural waste. And then probably another 200 million tons of forest residue. Together, you have close to 750 million tons of agri-waste. And these are rich in both aliphatics and they're all also rich in aromatics. That's really important because if you really look at our current set of polymers we have in the market, aromatics play an important role. Roughly around 40% polymers are aromatic in nature. Yeah. So you need to look at both the pH bonds. You need to also be looking at what are those aromatic rings that are available in the biomass, which I can really use to build my future polymeric materials. So I think as India, we need to really take that opportunity and all of you who are already working on biomass related programs, I think you are really on the right track, continue pursuing it. But one element what I really want to highlight is that if you go to industry typically tends to be a bit static in nature. You really want to make polyethylene. You still want to make polypropylene. Yeah. There is no great drive at this point of time to move away from that, looking at the cost structures and the risks associated with the technology. So we need to really keep in that mind. And the key element there is to really build those connections within, I saw that chart where you are leading multiple centers of expertise. I think that's a great way to go in that direction. We need to really connect competencies. It doesn't matter whether it's a private institute or a public institute or an academic institute, because all of us really bring so many capabilities. And then we need to start really looking at lignin, all the bio-based materials, not just for fuels. I think if we do over focus on fuel, I think we are just wasting all the value of biomass and just leveraging only the energy value. I think that's really not the right thing. So one advice I would really give to all the students who are really working on biomass is to take a portfolio view. If you look at, people are already doing a whole lot of things. People are actually replacing fossil phenol with phenolics from lignin. And those technologies are commercialized. People are using biochar. I think, again, Mr. Rastogi talked about biochar. It's a great opportunity to enrich soil and reduce dependence on imports. People are making a lot of polymeric materials and carbon-based fibers using lignin, essentially fractionating it arranging them in a way we can actually build fibers. So my kind of plea to all of you is to take a step back, whatever you are doing, and take this portfolio view in terms of what are those 3, 4, 5 products that really maximize the value of this entire biomass value chain. If you put over focus on fuel, I can tell you, even with Gen 2 ethanol, the world hasn't made a lot of progress. We are struggling with it. The cost structure simply doesn't allow. Yeah? So we need to look for alternate ways where we can valorize all these ingredients of biomass, and then also push back the industry when they say, hey, you do everything, but you know what, give me an ethylene molecule. That's also insane. Maybe it makes sense in the short run as we really transition, but you need to be looking at materials and products which really make sense for the future, which are really carbon neutral and which are really carbon sink. I'll give you an example. People are making quite a number of panels for building and construction using polymerized lignin. Yeah? And you can just create the necessary porosity and then make insulation panels. They're really going to be great carbon sink. So these are all the opportunities. And I see that as IIT and as all students, you're already on the path of energy transition. So I don't think I'm really going to suggest you to do something very different.
Thank you, Mr. Murthy. It was really nice listening to you about energy transition. And now I would like to, I think hydrogen has been missed so far, and we have Mr. Parag Sepe to talk a bit about hydrogen. One of the important point of why we want to discuss hydrogen, and later we would also discuss batteries, because these are the 2 prime sources of storing your electrons, which you are going to generate from solar panels. Either you have to go through hydrogen route to store that energy, or you have to do it through batteries. So batteries will take up later, but we'd request Mr. Parag Sepe to talk a bit about hydrogen, the different colors which hydrogen has, and what do we really need to right away go into green hydrogen, or we should transition from gray hydrogen or blue hydrogen to green hydrogen. So let me hear back from him in terms of production of hydrogen and storage and transmission of hydrogen, both of these aspects.
Thank you for having me here for this panel discussion. So just talking about the green hydrogen, or before I go to that, maybe just giving background, where do we stand in terms of the so-called CO2 emission, although we heard that CO2 is not the only pollutant or the only greenhouse gas which is emitted, but definitely contributes substantially, sheerly because of the volume of this CO2 which is emitted into the atmosphere. 2 slides. So we are experiencing roughly 1.2 degrees temperature rise in the 20th century compared to the century before. And this rise of temperature is obviously because of the greenhouse gas emissions, and CO2 being one of the major contributors to that. When I look at India's CO2 emission, can you go slides further? So this is CO2 emission in terms of different industries which put CO2 into the atmosphere. So as you see, electricity and the other heat producers contribute to about 50% of CO2 emission. The next major contributor is the transport, which is about 13%. And then the industry, which is utilizing this hydrogen or utilizing this hydrogen plus the related products like ammonia. When you produce, you put a lot of CO2 into the atmosphere. So these 3 industries put together, we have emission of about 85% of the CO2 what we presently have. Now, what could be the solution to this? So for electricity, presently, most of the electricity is produced by the natural gas or coal or sometimes by oil. This needs to migrate towards the green part. Green could be based on the solar, wind, tidal, any of these forms. I don't say that everything will get converted into this form, but there has to be a slow transition in that direction to reduce the CO2 footprint coming from this industry. The transport part can be shifted to the EV or to the hydrogen-based vehicle movement. Hydrogen-based vehicle movement coupled with the fuel cells when it comes to the actual driving of the car. So that is big area where transport industry can move in terms of reducing the CO2 footprint. The other industries like ammonia and all, they could also migrate to production of green ammonia, production of e-methanol, and so on, wherein carbon footprint can also be reduced. So these are the three industries where most of this carbon is coming from. Now, as regards green hydrogen, if you go to the next slide, and one more. Yeah. So green hydrogen is a very simple process. It is nothing but utilizing the electricity to split water into hydrogen and oxygen. So it is as simple as that. And then utilizing this hydrogen in combination with nitrogen or CO2 to produce various chemicals. Now, there are different technologies which are possible for production of green hydrogen. One is alkaline water electrolysis. Another is proton exchange membrane or PEM technology. And the third one is SOEC, which is basically high temperature splitting of water into hydrogen and oxygen. Different technologies are at different maturity levels. Probably alkaline water electrolysis today is the most mature technology to produce green hydrogen. And as ThyssenKrupp, we have developed this technology. We are selling this technology. And as we speak, we have about 2.5 gigawatt worth of hydrogen projects which are under implementation, not under discussion, but actually under implementation. Now, what is the key for hydrogen to replace the other fossils or find application in ammonia or e-methanol and all? Obviously, is the cost of production. And most of this cost of production of green hydrogen comes from the electricity. About, depending on, of course, the capex, but about 70% of this cost is based on the electricity price. So if you have electricity, which is available at, let us say, 2 rupees per kilowatt hour, and 70% is the cost of production of green hydrogen, you require roughly about 50 or 55 units for 1 kg of hydrogen production. So at 2 rupees, let us say you get 110 rupees as your OPEX, and additional capex on that of 40, 50 rupees, you can produce the hydrogen at 150 rupees a kg, which is even more economical than the gray hydrogen what you produce by conventional steam methane reforming, which cost today maybe in the range of 150 to 250 rupees, depending on what is your gas price. But the challenge is how to get sustainable, renewable electricity at 2 rupees per kilowatt hour. Probably solar has come down already from 12 rupees, maybe 20 years back, to even cost of production of 2.5 rupees per kilowatt hour, but only when the plant runs. And the unfortunate part is that the sun is not available 24/7. So you require in between energy banking and release to make it 24/7 available. And that increases the cost of the sustainable energy which is coming. But in some countries like Saudi Arabia, where we are working on a project of 2 gigawatt, there they are able to produce electricity at even lower than 2 rupees per kilowatt hour. And that energy they produce in combination with wind, with solar, and with certain energy storage. And with that, this plant in Saudi Arabia, which produces green hydrogen based on alkaline water electrolysis technology of ThyssenKrupp, is actually standing commercially on its feet without any aid coming from the government. In the US, the transition is happening towards more the blue part, and blue in terms of ammonia, I would say, because they have a big possibility of carbon sequestration. So all this CO2 which is captured there, they are able to sequester it, and they find that more economical. On the other hand, US government is pushing a lot of subsidies into this, and that's why it is economical. To the tune of $2 or $2.5 for a kg, subsidy is already announced by the government, and that makes the project viable. So like solar, initially a lot of governmental support would be required to push the industry to make it viable. And then as you grow, with the learning curve going up, probably the cost of production would come down. Now, the problem of having hydrogen is once to solve by, of course, the cheap energy, but it doesn't stop there. Hydrogen is very difficult to transport. So when you produce this hydrogen at places in the world where it is economically feasible, not all consumption is centered at these places. So you require an energy carrier, and hydrogen, if you just convert from its vapor form to liquid form or cryogenic form and then transport it, you will lose about 30% of the energy just for conversion into liquid. So another cheaper alternative is to convert it into ammonia. And now you might have heard also that ammonia is talked about new oil, or the oil of the future. So this hydrogen can be converted into ammonia by using the nitrogen. Again, just separate nitrogen from the air by air liquefaction and separation using renewable power. So you produce then the green ammonia. You transfer this green ammonia to the place of use, and ammonia transport is very easily achievable. Worldwide, there is millions of tons of ammonia getting transported by ship from one place to another. And then you convert this ammonia back into hydrogen at the place of use. And then this can be used for e-mobility and also for production of ammonia or any other chemicals at the other. So this value chain, whole value chain is something which basically will bring CO2 reduction and sustainability in future. Thank you.
Thank you, Parag. It was really nice listening to you about hydrogen. And yeah, let me, I'm looking at the watch as well. We have 10 more minutes. We would try to finish it off within the 10 minutes time which we have. So the first, we have some academic representative as well. And I would like to go to Professor Priti Aghalyam. And I would expect her to talk about decarbonization of hard to abate sectors, including cement industry or steel industries. These are the industries which actually emit 7.5% of total CO2 is being emitted by cement industry, and another 7.5% of the total CO2 is being emitted by steel industry. And we do not see neither green cement or green steel is going to be commercially viable in at least by 2035. This is what is being projected. So, but even if it is being feasible in 10, 20 years from now, what challenges we are going to face and how we are going to proceed towards it, I would like Professor Priti Aghalyam to talk a bit about that, maybe in 3 minutes.
Thank you, Rajneesh. Thank you all panelists for very interesting presentations. I will stick to the hard to abate sector and also specifically say that we are looking at the near-term future at the moment when we consider the hard to abate sectors. We are still hopeful that the completely green cement, the completely green steel and transition to that will happen, but it's not going to happen today. It's definitely not going to happen tomorrow. So in the interim, we're looking at maybe at least the next 3 decades, I would say. What can we do and what are opportunities and challenges ahead of us is, I guess, the topic for the next 2.5 minutes of mic time that I have. So first of all, if you look at cement as a special case, every 100 tons of cement that we produce emits a lot of carbon dioxide, more than 90 tons of carbon dioxide. And this is from also, it's a what you can think of as a double whammy as far as cement is concerned, as some of you would know. One is that the CO2 emissions are coming because of the requirement of heating and energy and electricity, which is there inherently in many processes, and more or less that's what we've been talking about in this panel as well. But in addition, in case of cement, to make cement, as of course you're all chemical engineers here, you know, a little bit of the composition of cement. To make cement, obviously you need calcium carbonate. And when you process the calcium carbonate en route to making cement, you emit CO2 as well. So this double whammy of carbon dioxide emissions inherently in the process and for the heating and other electricity needs of the process make this a genuinely difficult to abate process, not just in my view, but that's what we are looking at. What are the opportunities for us in this? assuming that we can't really avoid either of these emissions. First of all, as spoken about through the course of today, we need an ability to capture the CO2 that is being emitted. And secondly, find a way to do something with the carbon dioxide that's emitted. Now, Rajneesh has also previously talked to you about the sort of the magnitude of the CO2 problem, and which is why I also mentioned that for every little bit of cement that you make, almost the same little bit of CO2 is emitted. So you're looking at a massive CO2 problem that has to be addressed. So if you're going to store it or utilize it, you need a solution that is truly massive and scalable. There are several options that people are looking at. The utilization option, where you try to take the captured CO2 and make something from it, including building materials that were talked about, I think, in the Q&A session previously, is, I believe, a small opportunity. It's maybe about, at the most, 1/10 of the CO2 can really be addressed in this way. And within that 1/10 of the CO2 of hard to abate sectors that you can address, options are to, of course, go with the chemical engineers' bread and butter and make chemicals. Lots of our chemicals, as we discussed in this panel before, need carbon. And let that source of carbon be this captured CO2 from the process. So there is that opportunity. Aside from that, and specifically in that, I think methanol, making methanol as a potential fuel is emerging as something that we should look at. Other things like making materials that give structural strength, etc., are also being explored. But more than all of these, finding a solution where you can store the carbon dioxide safely is, I believe, the only thing that is going to address this problem at the scale that it needs to be addressed. I'll just say one last thing. I'm sure that my time is almost done now. Whatever the solutions that we are looking at, and this is sort of the philosophical standpoint my group is taking, whatever it is we are looking at, we believe that you have to look through the entire value chain. Don't just again, chemical engineer, so I can use these words, don't just draw your control volume or your system boundary around a solitary cement plant or even your electric vehicle. If you genuinely want to address this problem, we have to really look at the entire system. So if the cement plant is emitting carbon dioxide and we are using that carbon dioxide to make a chemical, what will we do with that chemical, say methanol, and in the entire life cycle of this carbon as it courses through our systems is what one has to look at and sort of say whether the solution is a good one or not. So this is just a couple of viewpoints that I wanted to share. Thank you.
Thank you, Priti. It was really awesome. Maybe you can. Yeah, so now I would like to call on Arvind. He has been silently listening to all of us. But I am sure he has some very valid point. But before he starts, I'd like to put the context here. See, what Priti was telling about is that we should identify our control systems. And if, let me tell you, most of us are thinking that EV, which we are going towards, it is solving our problem, but as of today, it's not. Because the electricity which, let's forget about the batteries which was produced to run this EV, has already significant large amount of CO2 footprint. But the electricity which we are consuming to charge our EVs are coming from coal. Otherwise, if we were using ICE, means internal combustion engines, it would have come from oil, which is lesser CO2, has a lesser CO2 emission compared to coal. So as of today, if we are going to EV, we are actually increasing our CO2 footprint. So based on this, let me quickly ask Arvind that all the solar energy which we are going to produce or the energy which from the air is going to come, wind energy, what are the challenges we are going to face to store these energies for really long time? In case of solar, we'll have to store it for next 18 hours before the next sun rises. And in the case of wind energy, we will have to store it for probably 4 to 5 months. So now these two are very big challenges. One has to really understand the complexity of this if we have to really go to completely renewable energy. And I would like Arvind to not take more than 3 minutes to please explain what exactly are his thoughts on this.
Thanks,
problem.
Rajneesh. It's a bad part of being the last part of the panelist section, but anyway. So I think it's been really a fantastic discussion since the beginning on various topics. So coming to this energy storage, it's actually $1 trillion question, Rajneesh, that you've asked for. The thing is that I kind of counter argue on the statement that you've made because we are emitting too much based on the EVs, like when we use batteries. The thing is that we cannot develop all the renewable infrastructure first and then start looking into the batteries, because I have a feeling that those are two independent research or implementation activities which has to go hand in hand. However, I think the target will be reached only when the renewable integration to these batteries happen 100%, then we go to literally net CO2 emission on the operation side. Of course, the emission during the manufacturing is something that we'll have to really look into. And I think somehow we have gone to the word net zero, and almost all our students also really get biased by that word. I would use the word, rather than net zero, I would use the word reducing the carbon emission, because I think we both analyze together. We are emitting 3 billion tons of carbon dioxide now, and based on the economic growth and population growth, India is going to emit 3 times more by 2047, which is 100 years from independence. And we are more worried about the CO2 that's going to be emitted in future, not the ones that are already emitting. So the ones that are already emitting anyway will be phased out. The ones that are going to emit are the ones that we have to seriously worry about. And I'll make a last point and stop. And almost every panel discussion, anyone who is sitting in the panel will give really a lot of nice thoughts, and we get a lot of questions as well. We have industry like representatives, academics, including students and faculty members. Can we do cumulatively something at the end of this discussion or end of this day, or take something forward even tomorrow, day after tomorrow, or sometime by the end of this month, and take some concrete action plan? Because merely talking, and then I'm sure all of us want to do something, unless we put all our efforts together in one place. I'm sure individually, or like every company is working with some faculty members or the other in some part of the country. Unless we come together, we are not going to really solve the problem. I think this is not only specific to this panelist. In fact, for all the other panel members from other panels as well. I think can we come together and do something at the end of this change session? That would be the best outcome we can make. Whatever the intentions we have, unless we put into action, we are nothing.
Arvind, nice. But before you stop talking, I would ask you one more point. You have been working on this zinc air battery, and I'm pretty sure many of us are not aware of this. Could you please talk about zinc air battery and what are the importance of this for next 1 minute?
Sure. So when you want to store energy for a few months, do you find a way out? The answer is no. You can take your mobile phones and charge it, give it for 1 month, come back, you'll end up with 50% charge. And so if you want to take the energy from May and then use it in December, either we can store it in the form of hydrogen. I think that's the best part of it. If I store the hydrogen in a 200 bar pressure cylinder, roughly 1 kg takes like 57, roughly 60 liters, I'll put it that way. The same volume, if I store it in the form of metals, and that's where the zinc air battery comes into the play, I store 8 times more energy in the same volume and with at most higher safety. So the energy requirement is fairly large. I'm not trying to say hydrogen is good or zinc is good. And I believe that everything has a market, and that's where we work on mechanically rechargeable zinc air battery. Chemistry is not new. It's the engineering aspect of it. To store the energy for months and years together can be achieved when we store the energy in the form of metals. And that's about the zinc air batteries. Thanks, Rajneesh.
Thanks, Arvind. So I am running out of time, but still we have one more topic to be discussed, and that is basically electrification of chemical processes. Because in the world where fossil fuel energy is not going to be available, and you have to rely mostly on electricity, it's very important for us to understand this is a big transition. Right now, most of our processes are optimized to run on fossil fuels, on energy. Basically, this is heat energy. Now, if we have to convert those processes into electrons-based energy, then we are going to have a huge amount of challenge. And this is why I would like to basically bring in Professor Himanshu, and I would expect him to talk a bit about what exactly he sees the challenges in this transition from fossil fuel-based processes to electricity-based processes.
Thanks, Rajneesh, for the question. So we hear a lot about electrification of transport sector, and similar to that, there is also some people in chemical academia are looking into electrification of chemical industry. As you mentioned, we need primarily heating of
all this process is to convert raw materials into products. And that heating primarily is driven by fossil fuels. So now people are trying, instead of fossil fuels, can we try electricity to heat those processes and reactors? So some technologies are mature to do that. For example, our kitchen microwave oven, most of us have that in our kitchens and we have used it for several decades. Now the question is, can we use the same technology in chemical industry, and instead of burning coal and other fossil fuels to heat our reactors, can we directly use these microwaves to heat up the reactors and convert raw material? Now, fortunately, when we use microwaves, along with this ability to use electricity, there is another possibility of process intensification. It has been observed that when we use microwave heating, many of the processes, the output is much better than using conventional. And that angle of ability of achieving process intensification as well as ability of using renewable electricity in future gives a big hope in the chemical industry to look into this microwave heating of chemical process. Now that is one major goal or one major direction of electrification in chemical industry. Other people are also trying other forms of electrification. For example, all the electrochemistry is based on electricity. If you look at it, we are using electricity to drive a chemical process, whether it is converting CO2 into formic acid or syngas or producing hydrogen from water. That is another form of electrification, as well as using direct joule heating and other forms. So it shows a lot of potential. And I think industry also should try to look into this aspect, not just academia, that how can we leverage electricity directly into industry like transportation sector. And one specific application of that, since we were discussing about hydrogen and Mr. Parag already talked about ammonia, is can we, instead of storing hydrogen, liquefying hydrogen and transporting it, can we convert hydrogen into some chemical form, either ammonia or methanol, and then transport it because it's in liquid form and we already have infrastructure and technology. And there also we have seen really nice developments. For example, when we use microwaves, people have observed that we can reduce the pressure required to convert nitrogen and hydrogen into ammonia to close to atmospheric pressure, which is a big challenge right now. Because if you want to produce ammonia at small scales, right now it's not economical using the traditional process. We need to come up with some groundbreaking new process design that can be used so that we can produce this ammonia at small scales near a solar farm or wind farm, for example. So these kind of new, I call them new degrees of freedom that chemical engineers have, that can we use our chemical engineering knowledge plus these new ideas of microwave heating, electromagnetic waves, plasma, into the traditional chemical engineering and come up with some new process design which is meant for our sustainable.
Hey, thanks. I'm running out of time, but I have not engaged with the audience as yet. And I would like to engage in a different way. So I have a quick question for all of you. What do you think, how much cost we pay for per liter of water? We are talking about sustainability and stuff. So let me ask this quick question. What do you think we pay for per liter of water we use? There are many engineers, you should know the cost. Per liter of water? No, per liter of water, industrial water, say fresh water, which industry might be using. They might be able to tell us a number, but typically what is the cost of water which we pay in industry? It's 5 paise per liter maximum. I don't think we pay more than that. But let me give you a small information. To produce 1 kilogram of sugar, you know how much water is consumed? Roughly 2,500 to 3,000 liters. So the water cost itself is roughly 150 rupees. And we are paying only 40 rupees for the sugar. So please be aware that sustainability does not come at cheaper price. So if there is a question of getting electricity at 2 rupees per unit, if your electricity is going to be sustainable, you can never get it at 2 rupees per unit. This is something which you have to always understand. Every processes, we count the numbers. We do not really count the numbers for the pollution which we have created. The water we use, the CO2 which we emit, and all these calculations today are done without calculating the sustainability aspect of it. So if you are expecting that the cost is going to go cheaper and still will be sustainable, that is not the right expectation. So this is what I would like to end this particular talk with. CO2 capture and sequestration will also come with at a large cost. And among us, we have to agree that we have to pay for it. No one else is going to pay for it. If you have to keep this planet alive for next 100, 200, 1000 years, we will have to pay today. We cannot keep waiting for it till next year or till 100 years down the line. Thank you very much for attending this session, and we are having a lunch. So please enjoy your lunch. I will now request Professor Priti Aghalyam to give a memento for an appreciation for all the invited participants over here.
Thank you. Please join us for lunch. The back will regroup here by close to 2. The next session is scheduled to start on advanced materials. It's moderated by Abhijit Deshpande. And thank you also for enduring the temperature in this room. It's a peculiar chemical engineering problem, I guess. I think with the open atmosphere, doors opening, the AC is trying its best. And this is kind of solutions that we are looking for as in our profession. Thank you very much.
Thank you.
Just a quick, just a minute while you're getting ready for lunch. I have a team from the IIT's student body, Team Raftar. They have something to tell you.
Hello, all. I'm Harish from IIT Madras, part of Team Raftar. So we are a student team, have been building electric and combustion race cars for about 10 years. And currently we also hold the world record for fuel efficiency for any endurance event. And we take these race cars to international competitions and represent IIT Madras there. And now in the process of building efficient race cars, we have realized that we have built a lot of technologies that can be used for sustainability. And currently we're looking into evolving into a national platform for electric sustainable mobility. And for as discussed in the panel as well, as energy storage becomes more and more relevant, managing batteries is something that's very important. And we are currently working with professors and in academia to build battery management systems which are smart and which can not just predict algorithms, but not just react to faults, but also has algorithms to predict faults. And we're also working in charging infrastructure, building sustainable charging infrastructure. And our vision is to build into a platform and connect both the industry and academia. And we feel this is the right opportunity to connect with the industry and onboard as many industry partners as possible. And we really thank professors from IIT Madras, especially Professor Arvind, who has been helping us a lot in this. And we really would want to onboard as many industry partners as possible. We would like to connect with all of you. We really thank the IIT Institute as well as the Chemical Engineering Department for giving this opportunity. Thanks a lot.
Yeah, please go ahead for lunch.
Thank you.
For us to start our next session. You can bring whatever you have food to the table and continue here. So have that opportunity in this venue. So welcome to the first panel of the afternoon, the two panels. This is on advanced materials. Moderator is Abhijit Deshpande. Hi. Good afternoon, everyone. We'll start. Professor Jitin, our panel members, Professor Jitin, Professor Raghuram Chetty, Dr. Karthik Kumar, and Mr. Seturam. Please. So I'll just give maybe a minute for people to come in. Very informal. Yeah. No, because this is lunch, post lunch. So we've had panel discussions in the morning, and so follow up in the afternoon is also panel discussions. This one specifically is on advanced materials. And it's my pleasure to welcome the panel members. We have Mr. Seturam. He is the Managing Director, India, and General Manager of Celanese. And he has over 30 years of experience in Dow, in Roman Haas, and starting out with Harita way back. The experience is also wide in terms of the type of materials, emulsions, coatings, adhesives, specialty chemicals, and now focusing on engineering plastics. So welcome, Sejal. We have Dr. Karthik, is the R&D Director of Saint Gobain. He also brings 25 years of experience with right now at Saint Gobain, but earlier with Unilever, ExxonMobil, Reckitt Baxter, and again looking at wider cross section of materials, paints and coatings, insecticides, personal care, of course, with Unilever. And then now focusing on performance plastics. We have Professor Raghuram Chetty with us. His areas of expertise are in electrocatalysis and fuel cells and wastewater treatment. And he's also tried to combine both of these. For example, one of his recent work is where fuel cell is being used for chromium remediation. So combination of both sort of energy and wastewater treatment. Also looking at nanoporous filter media and other materials which are useful for water treatment. And then Professor Jitin John Burgess mainly works in the area of computational catalysis, also looking at carbon dioxide and biomass utilization. Recent work includes challenging reactions such as understanding dehydrogenation of propane, also looking at MOF, which is one of those materials which over the last decade a lot of interest has been there. So with this panel, we hope to look at the field of advanced materials and its relevance for chemical engineering. And to begin with, each of us will speak for a certain amount of time, and then we will have some set of questions. And then at the end, we hope to get some questions or possibly answers from you as well. If you look at materials as such, I mean, the materials up close, from getting it in the morning from toothpaste, personal care products, to, the chair we are sitting on. I mean, our materials up close are always there. Then we can also look at another big class of materials, which is sort of materials for society, in the infrastructure, transports, so societal importance materials. And we also then have an important class of materials which are in industries. They may not have a direct use or as a consumer or as a society, but may get used during our industries, so industrial materials. So, and if you look at materials as such, there is some very sort of showcase areas always. So one can think of space, and immediately research in space has led to a lot of advanced materials because weight is such a premium. On the other hand, of course, these days we also see mobile. And, there will be so many stories associated with materials being used in mobile being discovered for something else, but now mobile becomes possible because of those materials being utilized in mobile. So we have the overall scope of materials as a very broad spectrum. So to begin with, let's get a perspective from each of the panelists. So may I request Dr. Karthik to sort of just start.
Thank you, Professor. And like you said, let's face it, we are all materialistic. People have to be materialistic. We can't live without any such things. Today, as he explained, in a lot of areas, materials touch our lives. And it's good that as a R&D center or a student, you are able to take understanding materials in the different perspectives. I come from Central Main Research Center. We are famous for known for glass, but we also make abrasive refractories, performance plastics, ceramics, and other materials for various applications, from consumer construction, mobility to aerospace and various applications. So before that, I was with Unilever, where I was also associated with some patents and also a little bit on electrochemistry as well in the past. So it's good to come to this forum and understand more of these kind of topics and also contribute. When I look at materials, we were initially using materials by chance, which means whatever you had, we're using it for application which was available from that, for example, iron, steel, and other things. So as we moved on, we started optimizing that. I mean, we started making alloys, we started making things to suit our purposes. Then it became a little bit more complicated. We started to get plastics, other things, which really became a need of our. Let's keep this forward. One of the important things of materials is today we need to design our materials. We have plenty of options. We just need to make sure that the purpose for which we have is clear, and therefore we start designing those materials. Second point is, today, if I look at the past, we were having materials for quantity. We needed a large amount of oil or iron in this kind of things. Today, as we move forward, we're also going towards quality. We look at semiconductors. So therefore, if you reach advanced materials, we are actually moving towards a quality system. So there are two aspects which are quite striking from the materials perspective. Last but not least, I wanted to ask you specifically understand that today, when I am looking at materials research now in the center, we do not just look at this material as it was. like, you cannot just keep doing what different kind of glasses. I need to find, if you need a window, I can't just view glass. I need to also look at the frame, the system, the fittings, other things. And in addition to that, I have to enhance the quality of glass, the glazing and everything. So that if I start looking at materials research in the modern world, it's more like a system development. Yeah, and then within the context of system development, we certainly need to look at materials more like a formulation as opposed to use of virgin material. So therefore, our mindset should be, what can I make the original elements of the alphabets? How can I make words? How can I make words? How can I write rows of materials? That's the kind of ability to blend and design is what we need to have at this level. Thank you. Sorry.
So a couple of points that you mentioned and which is related to the focus on design materials. And then the other thing also which he gave an analogy was to sort of start from character. And so it actually helps to bring in Jitin at this stage because you know, what's the role of material discovery? And I think based on what he has to say, might add something to this. Thank you very much for that pointer, Vijay. So I typically look at materials and my fascination to materials are a completely different class than what you and I get to engage with on a daily level. So I'm talking about a class of materials that we commonly call as catalysts or catalytic materials. And specifically so, the materials that are called heterogeneous catalysts or solids. And for a chemical industry, these are extremely critical components, and these catalysts or solid materials are critical in shaping sustainability and efficiency of the processes. And efficiency and sustainability is something that we've been speaking about as part of the event today as well. So how do these catalytic materials shape up sustainability and process efficiency? So it can be thought about in multiple different perspectives. Let me put that out there and then go on to the question that Professor posed. So one of the things that can be looked at in terms of looking at sustainability is we heard in the morning sessions that we are looking at moving away from fossil fuel-based carbon sources, which means looking at alternative chemical feedstocks. And catalysts become a critical element in enabling such transformations to go from one kind of feedstock and economies based on other kinds of feedstock. So the same catalytic materials that are used for conventional fossil fuel-based processes may not work for the new formulations and new economies that we need to work around for sustainable development. That's one perspective. The second and the most important one, which gets a lot of thrust and focus, especially with research in my group as well, is to understand the chemistry of how these materials do what they do, the catalysis, and to kind of bridge the gap between the chemistry and the engineering. So these materials that I'm talking about are very peculiar because the same chemical, the same material can have completely different properties when they have different shapes, when they have different sizes, or when they have a chemical environment that is different around them. So for example, if you run a reaction with the same metal, for example, but made with a different shape or different sizes, catalytic performance can be completely different. So to understand this and the variability in performance that we typically encounter because of variabilities in, say, synthesis and reactions being operated differently, one of the things that have come about as changed in the last couple of decades is to look at modeling and simulation of these catalytic processes. And that's precisely where a lot of the research focus in my group comes in. So that brings in the idea of explanatory role of how materials and materials chemistry, especially on the catalyst, really impact the reactions that are happening on the catalyst surface. That's one part of what we look at. But the question that is posed specifically to me is more on materials design. So how exactly do we bring in the materials design aspect? So understanding the chemistry and what exactly is needed for a specific chemical transformation to happen, that is something that we are able to look at from an atomistic point of view when we are looking at these kind of simulations that we typically employ. And that specific understanding enables us to identify a specific combination of elements or specific features in catalytic materials without ambiguity, which we can then try to make and synthesize in the labs. So the explanatory role of computations brings in unambiguous synthesis of catalysts that are likely to be much better performance. The second dimension that I would like to also think about, and which is very large prominence, is the idea of even coming up with formulations that are completely not automatic. So computations do have predictive capabilities where combinations can be evaluated very easily and their performances can be predicted. And when a choice of a few classes of materials can be identified as promising, they can then be evaluated for more detailed understanding. So computations and computational heterogeneous analysis have brought about that capability of making and engineering or screening potential materials as a very big avenue before controlled experimentation has been done. I hope that answers the question. Yeah, I think that's a very useful sort of place to, there is a screening and there's a choice and selection that could be done. But as a requirement, somebody will have to pose it. So in terms of thinking about, what are the mega trends? Where are the materials required? How do we see this? So I think at this point, maybe it'd be nice to have.
Yeah, firstly, thanks for this opportunity to be here in this forum. It's been very interesting for me to listen to all the different things that I'm not really familiar with, but fascinating to hear the different viewpoints. So what I'll do is the industry is a very large industry. So I'm going to take one slice of which I'm familiar with engineering plastics and talk about mega trends that are there. And in each of them, I talk about what kind of what's changing and what kind of material and other requirements are showing up that might be of interest to this audience, but also something that companies are working on, the markets are requiring. So if I start with the four megatrends that we have identified, one is future mobility, the other is enhanced connectivity, third is the whole healthcare, medical pharma, and fourth, which has been mentioned many times today, is about sustainability. So if you take the future mobility, I think in the last 5 years, and maybe a bit more, there has been a discontinuity in the automotive industry that has hardly changed for 100 years. Right? Since Ford came out with the Model T, it's really with electric cars and hydrogen fuel cell and everything else, things are dramatically changing. And as things change, the kind of materials you need to meet the requirements of this change are also constantly evolving. Lots of discussion today on batteries. I mean, cathodes, the anodes, the electrolytes, the separators, they're all very different from what was there. I mean, if you just take that battery, there's a lot of heat generated. Thermal management systems, thermal conductive polymers are coming in a big way. The biggest weight of a car today is the battery by far. So if you can reduce the weight, and people are talking about carbon fiber composites and everything else, which you never considered in cars before. Right? You wanted like weighting, but you put glass fiber maybe. But suddenly you need all these materials because you don't want to reduce it incrementally. Automatic lighting assistance systems, that's the other part where lots of work going on. So very reliable control systems, very reliable materials that don't fail under any conditions. So I think future mobility, that's several examples there, and I think that material space is going to continue to evolve. If you take enhanced connectivity, so 5G versus 4G is a complete setup, and IIT Madras is doing some wonderful work in 5G, right? And it's really developing the local indigenous 5G, etc. Materials required for 5G are not the same. When you think about being able to tune plastics to find the right combination, just simplistically of dissipation factors and dielectric questions. So antennas need a low dissipation factor. not antenna, sorry, transmission. Phone antennas need a high dielectric for reasons for asking what it is. So, you can take a look at this polymer and can you fine tune your requirements to meet that? And so on. So there's a whole lot of new developed materials that are being developed by the industry to meet the requirements of this. And now we're talking about 6G, take it to another level. Healthcare is changing in its own, I would say more gradually than the first two I mentioned, but yet it's moving. An example of healthcare is an implant, for example, that you can put in a medicine in a small rod of 3 millimeters of EVA. It gets injected into your body. And that delivers the medicine for 3 years. You don't need to take regular. So imagine patient adherence is not a problem. I mean, it's how many of us like taking medicines every day? Nobody, right? How many of us miss our medicines every day? But the same thing, if it's injected left there for 3 years, yeah, you can do it for 3 months, you can put it in your eye, you can put it, there are tumors where you can insert this implant, and instead of taking chemo all over your body, you just deliver it exactly where it's needed. So these are all some of the new development that's happening there. And finally, sustainability. I mean, I think one of the engineering polymers, I believe, are a very difficult problem to solve with sustainability. Because by nature, they have to be durable, they have to last long, they have to have great properties. And then you suddenly start saying, wait a minute, after using it for 2 years, I want them to just disintegrate into the ground. So what are the options you can use? And there's recycled materials, and we were talking about e-waste recycling a little while ago. You can do what's called biomass-based materials. So you start, you keep the finished properties the same, but you start with biomaterials. So biomethanol gives you a polyacetal, which has exactly the same properties as a fossil base. But you're starting with biomaterials, the carbon footprint is less. Similarly, carbon CO2-based technologies, a lot of discussion today, versus starting with carbon monoxide. They're a C1 chemistry, and our starting point is carbon monoxide, methanol. So instead of that, if you can start with carbon dioxide, that's the one. And of course, there's the biodegradable bio-based materials. So I think there's a lot going on. It's an exciting time, I believe, for engineering plastics. And as Sarthik mentioned, I don't think these problems can be solved in isolation by industry. I think we are beginning, we're traditionally been very insular, but over the last 3 years, we're engaging, not like in India, because we don't have an India platform there, but globally, very strongly with academia in order to enable this. Thank you.
Thank you. Thank you. So we already heard, of course, in the morning, we heard a fair bit about energy, and focus of this panel is on materials, but we already sort of also start talking about sustainability. So to bring these three together is actually area of Professor Raghuram. So I request him next to speak about it.
Yeah, I think today this panel is discussing about advanced materials. I just wanted to say, our human body is an advanced material. It's a material which nature has developed over several thousands of years, which we have in our hair, or our skin, or our nails. So everything is an advanced material. And each of them has, its own function to finish. But also, we have temperature sensor, which regulates our body temperature. We have pressure sensors, which regulate our body pressure, and so on. So all of that is what we try to mimic in our chemical reactors or reactions. And we want to control our temperature, control our pressure, and then carry out the reaction with isothermic, and so on. So in this process, the materials have always been materials or years. And one of the things I wanted to talk about is fuel cells. So fuel cell act in a very similar way how the human body works. So it takes fuels, similar to human system where we go for food, and we take oxygen, we breathe oxygen, and we go to combustion. So similarly, the fuel cells also take up oxygen. So we have the fuel here can be a hydrogen source or a new source which contains hydrogen. So we have hydrogen as a fuel and oxygen as an oxidant. So that gets used up in a reaction we call as an electrochemical reaction, and then it produces electrical energy. So in that process, there's an exothermic reactions where the temperature is also has to be maintained and the pressure also has to be maintained. Very good power what we want. So this has a human connection, whatever the fuel cell what we talked about earlier in sessions are also now. So they have a human connection in which it has developed. So this advanced material, if you look at, so this was invented close to 1830s. So before that, there were electrolysis, which has been made from 1800s. So after 20 to 30 years, people do electrolysis, I think people started to think about it. I think William Gray was a scientist, we thought, so if water can be split into hydrogen and oxygen, can't we do the reverse reaction? So can we not combine hydrogen and oxygen with water? And in that process, can we also get electricity out of it? So that is where this curiosity of fuel cells started. So at earlier time, the water electrolysis is generally done using platinum or noble materials. So we have platinum as a catalyst, which is used for this reaction to split. So he used the same platinum catalyst and he combined hydrogen and oxygen, and he was able to get electricity out of it. So that's the beginning of the fuel cell, how it started. But over the years, I think things have changed. Later, NASA wanted to use fuel cell for the space mission. So that time, they were looking at opportunities elsewhere to see how we can generate electricity on board using the compact system. Because earlier times, the only more batteries were lead-acid batteries, so which are very, very heavy batteries. So this NASA developed several research findings were given, and the answer they came up with was fuel cells. The reason was they had hydrogen, cryogenic hydrogen was there on the shuttle. And to send astronauts, they also had oxygen in their space capsule because the astronauts want to and so on. And so hydrogen was there, oxygen was there, and then the fuel cell is the one which can convert into electrical energy, and the electrical energy can be used for the covering auxiliary components in the space capsule. And also it produces water as a byproduct. So water can be used by the astronauts for their needs. And this is an exothermic reaction which also produces heat. So in this case, it's very cold, so we produce it as a heat source and we can warm the cabin and so on. And here there is no other waste is generated. So combining all of this, fuel cell was the best solution they thought to space application those days. And things have changed, I think, over the years. Fuel cell have reached from space to also land. Today, I think we talk about those advanced materials. So early days, platinum was used as a catalyst in a foil, as a sheet, and that was earlier times platinum was used. So look at the material development. So this platinum became porous platinum, and then they became nanoparticles, and then as you can talk about from smaller in size, we went from micro to nano size, and then the change of shape. So we went from spherical particles to different shape control particles, because each of the particle has its own ability to oxidize or reduce certain reaction, and certain things favor an oxidation reaction, and certain cases favor reduction reaction. So there is a whole lot of material development which has happened. That is where this advancement has happened. And today we can see that there are cars running on the roads. And that is one of the examples which came to India last year. So you can see that transition. The IC engines have ruled the transport industries for close to 200 years now. And we can see the transition going from IC engine to EV. So EV is a kind of a stopgap, I would say, that may be there for some years, but I think eventually hydrogen economies are adopted, fuel cell as a future mobility source. So I'll stop here and come back.
Thanks. Thank you. Thanks, Raghu. So, chemical engineers discussing materials within our department. Also, if you look at the materials research does happen under a fairly wider cross section. I mean, we have catalysts, of course, and membrane materials being mentioned. My own area is also in polymers. But if you look at the broader spectrum from our faculty in the department, many people are looking at absorbents, whether it's for wastewater treatment or whether it's absorbents for carbon dioxide sequestration. So a lot of us are also working towards material development for absorbents. And we have people working in semiconductor processing, people who are looking at foods. So there are several such sort of different materials that are represented in our own department. But my question to sort of both the industrial analysts is, what's an average composition of a team which is looking for, let's say, new material within your own organization? How do you build a team which is looking towards better material for a given application?
Firstly, I'm not the R&D guy, so disclaimer. If I look at our company, most of our innovation, again, this is different companies have different philosophies. Our company, most of the innovation has been outside in, especially over the last 5-6 years. We kind of used to do a lot of inside out, but we moved more to outside in. So in that sense, a lot of the work we do in new innovations comes from what the customer needs, listening to the customers. And then we bring in the talent that's needed to be able to meet that requirement. And our innovation, we call it technology and innovation, not R&D for various reasons. That team has what we call a mix of product developers. It has marketing people. It has program management people, because we have found those three to be very critical. When people are developing the product, people are bringing in the insights, and regularly, as you develop, you want to be having a cross-check, are you doing the right things? And program management, IT manages the program, ensures things stay on track for delivery. So that's what. Thanks. From my side, if I were to look at, having elemental level or fundamental level of materials, we would probably say less than 1%, where we actually, what we call as blue sky research or an element of industry where they would want to reinvest into finding something, it's about 1%. But the chunk of research happens in putting things together and what researchers would say as product development. Let me give an example. Today, if I were to have a plain glass, it has, of course, its own process, it has its own glass process, how to make it happen. But today, we actually coat the nano level, the 15 to 20 layers of stacks of material. So it could be silver, it could be, various elements in your there as a design element, so that it can reflect heat from the sun. Today, as a facade, you let the light in, but you let the heat out. I mean, that's the kind of design which happens. And we could do it by sputtering, you could do it by chemical deposition, you could do it by various other proteins to develop acidic conditions also. So when I look at materials for the specific applications, it could be like the analysis model, as Professor Jatin said, we could make more than about 20% of our composition as well. We have a gypsum board that we have worked with a lot of faculty here on development of gypsum board, specifically not because gypsum as such takes water, but when you want to put the gypsum board in your bathrooms, it has to be resistant to humidity and moisture. Now you get a problem statement which says, hey, I need a material specifically for that. Then we start looking at formulating these products. So that's about 20%.
Thanks. So the other question, which again, I will first go to my industrial participants before opening out further, is related to the training and teaching that happens in chemical engineering. And from a materials perspective, and specifically, what may be the kind of courses training that is required for when you hire a chemical engineer, but with materials perspective. So maybe I'll start with this case.
One thing which I got fascinated afterwards of a lot of materials and what was an individual materials is the ability to make composites. Today, we are not in a world where I can take one single metallurgy or polymer chemistry and make materials. Today, composites are very, very important. If I were to take, let's say, last fiber reinforcement concrete, one of the things we are working on, or if we are working on, various other laminates, addition comes in the picture. So you have to look at composites as an important future of making a new advanced material. So it could happen at the molecular level also, I'm assuming. So in that context, that's an aspect of academia I would probably would think about. And see how we can shape our studies into understanding composites as a materials part of it. Secondly, when I'm looking at this site like this whole symposium on sustainability, we at some point of time we're doing a lot of research to prevent degradation. I mean, I used to rush, we said, oh, let's paint something and then prevent us. Nature had a tendency to take back all the materials to its source form in some way. And today we are fighting to even do the reverse exactly. I mean, when we talk about sustainability, we are talking about durability, but today the durability has become far more than what the nature is. So I would say when sustainability in the context of today needs two elements. One is an ability for us to bring circularity. When we bring circularity, we talk about bringing in fuels, ability to bring the material back to the source of where we manufacture. So we are good at making things which customer want. We give it to them. The ability to bring it back and reprocess that is something which we're not good at. That's one element on circularity of materials. Second element is to design the materials so that it can actually unzip and give back to its elements. That's something which is an element of understanding which we all need to have. The third aspect which I would strongly urge all the students to understand this in the famous structured property relationship. When I say structured property relationship, we all think of this as one of the chapters in some subject, right? I mean, the ability for you to design some element of molecule and therefore get a mechanical or optical properties is just understood from what was earlier understood. But today, you have to be in a position to feed it. You have to be in a position to say, okay, I need this strength of so-and-so specification, but sorry, let me show this. Also, we have to have an ability to, have the feel for structure property relationship. And when you say structure property relationship, it has to encompass various traditional materials and the new materials which we develop. That's all the essence.
Yeah, thanks. So one of the things which I think I just wanted to bring focus a little bit back on catalysts, and so I just asked Jitin, especially in this area of structure property relations, what are sort of new directions within catalysis, or how is sort of different classes of catalysts which are being studied now and how these are important?
Thank you very much. So this is something that could probably take us with some examples. So structured property relationships from a computational point of view is kind of bread and butter for us. That's pretty much what we look at if we're looking at materials space, because that forms the background and the basis for us to be evaluating materials for certain specifics. And as I mentioned in my initial remark, so the basis for this is our atomic scale understanding of how every chemical bond transformation happens. So a particular bond breaks. Conventional catalysts were a single element, but many of the new age materials that we look at require related components that are different elements put together, which means every atom on that particular surface serves a specific function in the chemical reaction. So that information which comes from the molecular understanding of how the chemical transformation happens allows us to put together what was just mentioned as structure property relationships
which when we combine with known descriptors of catalytic performance, for example, in this particular case, then kind of translates into structure and activity relationships, which becomes a search space for us for looking at betterments of the same composition. Like I said, compositions could be different, so the same composition could behave drastically different when you have differences in shapes and size, or it could be looking at new formulations which are slightly different chemical elements put together in certain functionality. So if you know what exactly is required for a specific chemical transformation or chemical reaction step, then the search space is going to be based on this structure, its performance of the atomic arrangement with respect to its properties, and how that translates into a catalytic descriptor or a performance descriptor. For example, conversion or reaction rates, if you talk about catalytic reaction engineering, or selectivity to a particular product, if that's what you're interested in. So those performance descriptors, when they are coupled with the performance of the materials, will enable us to put together structure activity relationships, which becomes the basis for the search space, either in terms of formulating completely new materials and compositions, which have actually been done in numerous cases. So completely unpredictable compositions of materials put together have shown to be working much better than the individual components put together. So those kind of analysis, structure, property, activity, analysis, and relationships kind of form the basis for materials design for specific processes. Thanks, Jit. So we would, of course, mention variety of things which also have connections with our next panel. In the sense, we talked about sort of a very complex matrix of properties. We've talked about sort of prediction, sometimes which is on the basis of, let's say, the physics and chemistry that we know, but some other times may be driven by the data itself that we have. So there is a strong connection between some of what we are discussing and the next panel discussion. Also, there's one of the things that you also mentioned is related to composites. And again, the complication there is you're talking about multiple materials being involved. And one sort of strong feature in these advanced materials is to look back at nature to even start. So you can have biomimetic materials, or you can use natural materials themselves. I don't know if you noticed some 2 weeks ago, there was a big news about on the highway, the fender which is there, it's made of bamboo now, and it was sort of inaugurated by Transport Minister. So some things which supposedly we've been using for thousands of years, can we now adopt those materials for our current needs? So that's also a certain direction. But everything is always a moving target. So one of the things that I sort of wanted Raghu to talk to us about is the traditional materials, metals and ceramics, let's say, which have been really the backbone of our materials from early on. I mean, what is their current scenario? What way can we think of metals and ceramics for chemical engineering purposes and beyond also?
Right. One example I would take is the batteries. Batteries are what we are the transition what we are seeing. So it started, I think, if you look at the history of batteries from the World Cup, the first battery which was showcased, which people have used silver and zinc. So silver and zinc battery was the first battery which gives so later Daniel developed it to kind of take it to called as a Daniel cell. And then people have replaced, they get the zinc, but they replace the silver with copper. So here you can see there is a transition of metals like a low cost metal. I think people think about using high metals, which have a similar property, but it's still perform the way the battery has to perform. And then over a period of time, people have further developed the zinc battery which we use not these battery which have battery. So those are all primary batteries in which metals are used and developed. In the lead acid battery, so the lead acid battery in it is a rechargeable battery. We can charge it for several times. This development has taken in the early back. Then, when it's so they all had some environmental impacts. They were looking for other materials. They have been finding labs. So lithium ion batteries have been development and started from very early. So we coming to lithium ion batteries that we have. So we need to look at safety is another important aspect in it's not just to go into the picture, particularly materials, so people are outside, so we have different outside or materials were replaced out. So there are various chemistry which are available now, outside or and so on. So different battery chemistry were safer and also not too it's the problems. So that's where we can only carbon gases, so which acts like so here when a lithium ion battery percentage is very small. It's less than 50% is what is the lithium, and that is the lithium ion. It's not the lithium metal which is used in the battery. So, so the materials have changed. So the quality of the lithium ion battery, where only 50% of lithium is there, where all the rest is other metals. So we have metals are there. So, and how it end up further is now we are batteries will be and is not allowed so we have a lot of batteries which is produced they all sustainability or recycling says some battery has a raw material instead of so these materials can be used as a raw material and ready for other process which we have see batteries, but you can have other applications. So we can carbonate or use in other applications. So that means that value chain that can be because the metals usually we can get it back into the same metal and we can keep on using them in other applications.
So we've spoken quite a bit about sustainability and reuse. And as far as materials go, one of the challenges that we have is in terms of the spectrum of properties, which we have to optimize against. And on that, now we add this additional feature. And so my question to sort of both of you is related to, at least from what I know, there's a carbon footprint calculators are there. So for example, now already in terms of materials, do you already have these properties and then also a number for carbon footprint in your decision for selection of materials? So that's one aspect. And secondly is not necessarily maybe in your own industry, but do you have an example of a material which purely won it because of the number which was for carbon footprint or some sustainability parameter? So,
firstly, what you do, carbon footprint for us is one of the important parameters we evaluate when we get a new project. So, and when we then go to the next step of choosing materials, that does play a role. A lower carbon footprint always, and not just the material, the LCA kind of carbon footprint. So that's certainly there. I'll give you an example of where a customer chose a material with a carbon footprint. Maybe that will have it. So one of our customers, and this is public information, I can share it, developed a continuous glucose monitor, which is connected up to a mobile phone and does all kinds of things. So it's very user friendly. And they were very keen on having, I don't remember, a zero carbon footprint or significantly reduced carbon footprint.
And this biomass-based material that we gave them was medical grade, but it was one of the enablers for them to reach that. And they chose us because of that element. So therefore, customers are making the choice. Very clear. Yeah, yeah. Again, I refer to LCA. LCA is the life cycle analysis, and we have evolved in that from various aspects. Of course, carbon footprint is one of the various attributes which LCA calculates. I mean, there are very other aspects of the environmental impact that develops. Initially, we used to be scoring ourselves, okay, we are making better in water, better in recycling, etc. So there was like very quantitative way of calculating our audit. But then, of course, a very auditable quantitative way started coming in. We call it either as a cradle to grade or cradle to grade. As a gate. Because either which way, which you define that it could be scope 1, scope 2, scope 3. All these are something which you will understand from the sustainability definitions. But what is important is yes, most of our customers today are demanding sustainable products and close to zero products. So all the industries following the government and actually declaring net zero carbon in 2030, 2050 kind of a situation. So in that context, we have to be having products which are sustainable. So in that context, our journey is we start off with what we can do at our factories. So we move on from using coal-based fuel to solar-based fuel, start by using biofuel. Actually, one of the projects which we are working on that is biofuel. So all of this actually helps to get closer to net zero carbon. And some point of time, you have to formulate or start using less of it. My experience on that product, so is the previous company, where we used to use detergents and we went and sold detergents in 5 kg, 20 kg. People had difficulty carrying it from the shop. Yeah, literally, because it was filled with fillers and salts and whatever. So as an industry, we took a position to reduce all the aspects and we launched a small product, just for small and mighty, which is not local based, which is very easy to use. Unit systems, and then it started becoming law in especially Europe, and then it's now catching up in various countries. So maybe I think we can have, if there are any comments or questions from the audience, we could pause here and bring those in. Given the kind of comments you have made, yeah, this. So this is related to water treatment plant. And again, it goes back to my previous experience where the activated sludge or sludge, which is generated as part of this aerobic process, is very difficult to decide. So you all know that the PCB strict norms. So once it comes under hazardous waste, then we need to discarded through PCB approved vendors. And for discarding 1 ton of sludge, we need to shell out huge quantity of money. Like I can take one example where in Palakkad, while working with United Breweries, I was like shelling out 9,000 rupees for discarding 1 metric ton of sludge. So we had like almost 8 years back implemented one advanced material which really helped to reduce the activated sludge generation in the aerobic process. So that was quite a long time back. So we'd like to know, is there any recent advancement or any advanced material with respect to this aerobic process to reduce this sludge generation? But with respect to that, I have implemented one advanced material, but quite a long time back. So I would like to understand. So that is my question. So you want to add something?
Yeah, in sludge, I think now this material process, you can say material phasers are coming up in Otherwise, it's an safe, I mean, that could be one certain thing we use a slides. Oxidize or use of industrial use. In this process, we can also kind of consume the so which is generated, and we can also get some electricity out of it. Don't know the exact nature of the microwaves in this industries, but this is something fundamental study can be done to identify the what micros can be used to deactivate these clouds and put them back in use for. So then, but since it was a good forum to discuss, I thought of giving or sharing my experience where advanced material called PV Gel Beads. It is a Japanese technology from Kurare. The Indian representative was SBS Hero. It's a PV Gel bead. Just adding to that what Natik said, right? My experience is having worked with many materials, it's actually, I think, impossible, at least at the undergrad level, to reach everybody of the materials. I think you need to give them the basics and some of the things like what Alan said, economics and stuff that they do, of course. And maybe when internships or otherwise, get somebody to go deep into one material. Because then you know how to do. Because beyond that, you have to work together there. I don't think you can cover all the materials. Specifically in our department, we also sort of, we used to have a course which is called process design, but now we have process and product design. And so to bring in some elements of what we're talking about, which are sort of tied to materials more closely.
My name is Abba. Yeah, so I think we've reached the end of the time. I thank my panel members for I think what has been a very fruitful discussion. I've got some points for our department to also look forward to. And I hope that from your side also there are some things for taking things forward jointly. And I thank all of you also. Thank you. We're coming up to the last session on data analysis and process system engineering. Before that, we have a very short presentation by Dr. Dara Ajay, who is the Senior Manager, Technology Transfer Office, IT Management Cell of the ICSR office, talk about intellectual property management patenting. This Greetings from the Technology Transfer Office of the CSR. I'm Dr. Dara, in the Technology Transfer Office. Thank you very much, Professor Krishnan, for this time and opportunity to discuss the intellectual property management of the IIT Madras. Today I'm going to take you through how IIT Madras maintains the IP, intellectual property generated in terms of innovation capture and also in terms of commercialization of the same. We are the ICSR holds an intellectual property management cell which has two verticals. One is with respect to the capturing of the innovation in terms of IP, which is the IP cell. This cell has two verticals. One is in terms of operations, which will be taking care of the capturing and putting of the IPs which are being generated by process through a portal called Stella, and we have an online document system computer generated actually. And the processing tool called as analytics tools, who will be assessing the novelty checks for the invention which has been done. And these two tools will make sure that patent or the any of the IP which has been generated in the IPM success rate of 99% of the IPs which we find in the software. And we have 7 months is the shortest time that we can grant a patent. And once the patent is granted, it goes to the technology transfer office. The technology transfer office is the office who is responsible for the license negotiation. So we do the IP which has been generated in the IP, very thorough assessment. We have so work on it to stress outreach for an industry party for the interest of the licensing. And we will license the technology where we can help you with respect to the patent valuation, how much should be the value of the IP which is being negotiated, and we also do an end-to-end licensing from the thereafter the maintenance as well. So what we
as an ICSR, is we release the project management in all the projects, irrespective of whether an IT is generated or not. If there is an IT generated, there is involvement of IT cell, legal cell, and others. We have studio office, and other entities only associated. So, a very quick portfolio of the complementary patents. We have displayed a list of 42 patents available for licensing. And if the industry party is interested in any of these patents, if you want to license and explore on that aspect, or else if you want to do a joint development program with the faculty members, we have a faculty tool. We have a technology tool which is available at the office. You can collect those pamphlets and you get in connect with us, and we will set up a meeting the discussions forward. So this is how the list will be. Wherein we have various categories of techniques, not 6 or 44 techniques. And we have individual, so of that particular techniques, if you can select one or two of which we might be interested in, then it's called as the flyer, which is in detail of the details very specifically in terms of what are the unique applications of the technique. We will set up a meeting like we have already had flyers. So thereafter, we will set up a meeting to see if there is a possibility of association, not necessarily do the licensing. It could be a JDA, it could be a consultancy agreement, it could be a complete master research agreement wherein we are not sure of the project, but we have a number of understanding between the IIT and the industry partners. So what means of association, we can discuss and enter into that set of legal agreement, and we can facilitate that. And considering the time constraint, there is an online form also which you can scan code and get these soft copies all the patents that are displayed. These copies will be sent to the email IDs if you are doing a scan copy. Thank you very much, and thank you so much for the time.
Call upon Dr. Shankar Mason, the moderator for the last session. And Congress have demonstrated. Good evening, everyone. I'd like to call the panel members, Sridhar Krishnamurthy, Dr. Lakshmi, and Mr. Sridhar Narasimhan, who's there, and Mr. Raj Srinivasan, and he's here. So this panel discussion topic is data analytics, process systems engineering. We are looking at what this is. It will involve not just data analytics, but discussion on artificial intelligence, ML, machine learning techniques, and so on. They're all interrelated systems. And also, it will not just be restricted to process systems engineering, it will impact in all areas of chemical engineering. So it will be actually talking about the entire gamut of it's impacting in all areas of chemical engineering. That's possible. A very quick introduction to the panel members here. I have with us Sridhar Krishnamurthy, who is a 1984 BTech from Madras Chemical Engineering. Subsequently did his master's in energy technology from IIT Bangkok, and also did an MBA from Monash University. Yes, more than 20 years experience working in the steel industry, and currently is the MD of Andhra Steel, which has a couple of plants, one in Punjab, one in Punjab, and Andhra Pradesh, and Pole. Welcome. And we have with us Dr. Lakshmi Edishwaran, who is from Anna University, critical engineer from Anna University. I know her from 90s, so she was with me at the time, R&D Center, and she went and did her PhD from University of Manchester under Martin Smith, and subsequently had a significant stint in the chemical industry, GE, and health chemicals, and in fact, towards our CEO, which was founded by me and my colleague in this department. Currently, she is working with analytics. And from our faculty, we have Dr. Raj Srinivasan, who is a 93 BTech from IIT Madras Chemical, and this is from University.
And there's a particular number in the US, Singapore for over 20 years, almost 15, 20 years, before we decided to come back to his motherland. And I think 7 or 8 years ago, we first joined IIT in Nagar, and subsequently returned to the proper place, which is his alma mater, IIT Madras, which where he has been with us in the systems engineering area. And Dr. Surya Kumar Nathaman is a dual student from IIT Chemical Engineering, then to a student from Clarkson University, and joined us about years ago, and he has been with the systems group at IIT Madras. Welcome all of them. And so the way we are going to try to keep to the time as much as possible, because I don't want to try to you that the gates are closing at 4:45 because of I think the chief minister being in the campus. So if you have to leave, they have to actually do so. So we will not try to exceed that. So the structure that I actually proposed, and I hope we can maintain it, is that we're just broadly, I'm going to raise 3 questions, and I'm going to give every panelist a chance to talk about this party, and read off questions from there, for 4 minutes each, and subsequently, after about 45 minutes of this conversation, I think we will open it up for questions from the audience, and they will answer. The first thing that the main question that I want to ask the panel members is, data analytics has been used in the chemical industry since at least my university days, which is 40 years ago, 1980s. There's been a big pass in these exams, and so on. What has really changed? What are the kind of developments that are occurring in this area that makes us take a hard look at the subject matter all over again, and its impact on chemical engineering in particular. I'll first ask Sridhar to kind of comment on this before going out.
So just to give you some background, so I work in the steel industry, and as you know, steel industry is probably one of the most laggard and slow of new changing technologies, etc. Normally, new trends and way of doing things comes from auto, aerospace, petrochemicals, and then slowly percolates. Steel and cement are one of the last 2 industries to change. Having said that, the kind of company I am in, we make steel for the auto sector. So basically, our steel goes into engine components, steering, axle, transmissions on the body, but everything inside. So as you know, auto is going through a big change. Electrification, lightweighting, a lot of things. So that is kind of forcing us also to change quickly. So a couple of things, of course, as you know, steel is although chemical, I'm still learning methodology on the job. Basically, it's a combination of some continuous and some batch processes. And therefore, we are looking at analytics as a way to either bring more cost savings or increasing the quality of the product, or to be able to reduce the amount of defects that come in the process, and thereby produce more prime product, and obviously that also helps reduce costs. And we're also looking at analytics as a way to trace back and find where the fault happened if there is a customer complaint. So in order to achieve all these objectives, we of course in the plant have several, one is the PLC or the DCS, distributed control system in the plant that runs the different individual processes. In between, we have what is called an MES system, which basically passes on the tasks from process to process. So there is very little human interference, and all the parameters move seamlessly from one process to the next stage. And the third aspect, obviously, is the ERP system, which is capturing and giving us reports and things like that. So a lot of the analytics now, what we are looking at is we are capturing a lot of millisecond level information
at the MES stage. Right now, we are not utilizing the full power of that data. So we have several discrete projects. To give you some example, one project we just completed a proof of concept was predictive maintenance. So basically, we had a company that came in and put sensors on various rotating machinery, and over a period of, I think it was 12 weeks or 14 weeks, we collected data and we looked at how many times we can predict a certain plant stoppage. And of course, depending on the type of area of the plant, 1 hour can mean several crores of rupees. And not to mention the explanation to the customer why the product was late or whatever. So we are looking at analytics as a way to improve these areas, but also we are facing some challenges because a lot of the workforce is not exactly literate in these areas. Of course, one is there a remote mindset, and secondly, my IT team is running 10 blocks away, and I have to tell them you have to take the different users in the company to along with you. Otherwise, you create a solution, nobody will implement it. So a lot of effort is going in training and changing the mindset of the company, but we can see a lot of potential and opportunities. So we have done 3-4 projects, one in predictive maintenance, one where we melt the steel. Sometimes the steel goes off chemistry or off properties. And sometimes that off chemistry steel can go to some other customer, but sometimes it is just scrapped and put back in the process, which means there's a lot more loss. So there is a lot of potential in those areas. So I think a combination of business sense and applying the right tool is what we're doing.
Thank you, Mr. Siva. You pointed out a lot of interesting application areas of data analytics, and about maintenance and quality control and so on. I'd like to ask Professor Srinivasan, look at what kind of technologies that have been actually developed in the last 40 to 50 years that can be leveraged basically by industry.
Yeah, thanks, sir. Sure. First of all, pleasure to be here. It's good to see a lot of faces, both from industry and also our students and scholars. So, to get your question, Shankar, what kind of technologies? So, let me kind of give a kind of personal perspective. I started working with AI, machine learning, and so on, roughly 35, 38 years ago. I started something that we did in the early 90s. This was when I was doing a postdoc with a company called Honeywell in the technology labs. They all together a bunch of oil companies to form a consortium, and the intent was to deploy what we now call AI ML to an actual plant. So we started doing that at one of Exxon's largest refinery in the world. And the charter given to us was there's all this work which has been done in literature, all these papers which have been published, hundreds, thousands of those at that time. Can we apply any of these techniques to make our production smoother? So me and a bunch of others, we all got together, replicated one method after the other from literature, took the industrial data from Exxon and generated results. Some of them were good enough to go live on the plant. They remained live for, I don't know, a couple of weeks. And then something other came out and the operator said, you know what, I'm happy the way I was doing it without the input from this new technology. So that was kind of the feedback we were getting back in the early 90s. So the technologies were there. Which are the most common ones which we could get live in the plant in these days. It was almost immediately multivariate statistics. The theory has been well developed. Obviously, there are a whole bunch of underlying assumptions. So those of you who have done courses or who are familiar with multivariate statistics, we talk about something very stationary. We assume that the statistical properties of the data does not change as a function of time. In the case of a plant, plant processes exactly the same raw material or makes exactly the same product using exactly the same conditions for weeks and weeks on end. They have to change for whatever reason. Maybe the demand for the products are changed, or the quality of the raw materials are different, or they have decided a way to optimize the process to make it energy efficient or whatever. So the data
moves, statistical properties change as a function of time, and that's why the first generation methods, which originated from the statistics, did not do so well. I will take a leap 10 years into the future. This time I was doing a project with small refinery, single plant. They are not part of a big multinational chain like the Exxon case. Again, they had access to a huge amount of data. This refinery ran for 20 years of that time. They had at least 15 years of data. With the data, their limit was, can you help us predict this property? So this was soft sensor that we would call it today. The property that they cared about was something called the B90, which is a way to measure the quality of diesel as it comes out of one of the distillation columns. Same challenge was there, meaning that the crude that the refinery was processing day in and day out could change every couple of days or every week or so. But this time, the neural networks had improved somewhat. So as long as they were processing the same crude that processed over the last 2-3 years, we could get a fairly good response in terms of object prediction. New decade into the future, now early 2010s, the questions that we got interested in, that when industry started getting attracted to, was not relying only on the process, but now also in the supply chain. How do all the things that happen in the supply chain, my shipment is delayed by a week, how is it going to affect the way I schedule my process? Like how do I schedule my production, etc. And again, there are a whole bunch of technologies which could be used. Optimization techniques is one that we had good success with. And the challenge really came down to, again, are we able to describe in analytical terms, in mathematical terms, the complexity of the situation. Recently, so I'm taking my last shot in the interest of time. Recently, we had a conversation with a company. You can call it a chemicals company. But this time we're talking with that people working in their R&D labs. What does R&D labs here do? This company is handed over production of a particular chemistry. And we are supposed to figure out a way to produce this at scale, at tons of this specialty chemical every year. Technology is proven to work at kilo scale, 1 kilo each ton. Right? Now, in order to scale this up, there are a whole bunch of steps that this company does in-house. A lot of this is around, safety, optimization, and so on and so forth. It takes them months to figure this out, to a level of comfort that they are willing to now invest money to make it at scale. The questions they care about are, will there be a sustainability issue if I produce it at large scale? Are the chemistry that have been handed over, are they good enough to scale up, or do I need to do more experiments at different conditions to be able to be comfortable with environmental safety, etc.? And the question that we were asked when we had this conversation was, can AI techniques help me predict material properties or reaction chemistry when I increase the scale? Can I do a experiment or actually investing in labs to do a calorimetric study to figure out the safety implications? So what I'm in a nutshell saying, Shankar, is that process data is what we typically think about when we think about applying AI ML in industry. Yes, that's been the first generation. And I think there are lots of success stories that one can see about being taught in reality. Many of them are also well reported in literature. But more recently, other domains, including what has been the remit only of scientists, is now becoming available to data science. So I'm very optimistic. Thanks, Raj. I mean, we did bring out two important things. That is the importance of instead of looking at a process in a narrow way, we are now able to still look at the entire supply chain because the availability of data may be available real-time data on breakdown, transport, where the truck is actually going. All of this is now available back in GPS. So those kind of things, information immediately helps you to react much faster, which means the tools that we develop for that, certainly that's one area I can see. And the other one was saying also, whenever we build a process, we probably will
pay as much attention to the safety aspect, the environmental aspect. The previous panel also was discussing about this, the whole sustainability. Now we have maybe information, knowledge about the thing that we can, data can be generated through simulations and so on, which you can actually leverage in the design process of selecting the appropriate materials of the process chemistry and so on. Thanks a lot. Yeah, I just want to again go back to the industry person, Dr. who is working in hydroanalytics, to ask what are the kind of problems that they are actually getting from broadly the chemical sector and also from the manufacturing sector in terms of that requires the kind of technology developments in the last, let's say, 20, 30 years that we have used for solving these problems.
So we are actually working on a broad spectrum of problems. See, there is a tendency for some of the solutions to get commoditized. So, you start with prediction problems, you predict the age, you predict the defect, and then you have preventive maintenance kind of solutions. So there again, you have a lot of players who have gotten, who have very packaged solutions in that space, and those are getting delivered. Where we are facing a lot more challenge right now is in automating some of the processes, because we're talking about the developed world and the developing world. In the developed world, the manufacturing industry is losing its edge because of the manpower costs and so on. So there are a lot of projects which are coming from a safety compliance. Any area where you have human eyes monitoring either a throughput or monitoring safety in a plant, all those areas are now getting packaged for AI-like solutions. Raj mentioned about supply chain, right? So there is a focus to bring in some of the software level solutions, make them more enterprise related. So connected factories, right? So how does my defect in a software, how does my supply from, from a procurement perspective, how does it all disrupt the end commitment that I have to a customer? So there is that enterprise-wide solution that is coming. But I think one of the very key areas where we are seeing, especially in the last 3 months, or maybe it is just a matter of coincidences, the industry is losing. There is not so much of talent left in the industry. There were a lot of very good operators that were setting a lot of talent that industry was able to draw earlier. That's now become a big challenge. So how do you bring the knowledge of these people, the maintenance experts, the operators, how do you embed it into the analytics delivery itself? So there is a knowledge management component which we are having to build. We've done a lot of the rule-based knowledge, AI delivery in the past. But right now, we are focusing more on some of those knowledge management systems and planning and scheduling, which are not traditionally, coming from, the preventive maintenance like commoditized solutions, because there is a larger level customization which is required to get these solutions well. So again, like I said, a broad spectrum of solutions, and the borders are going on getting pushed as far as industry is concerned. You do something and then they want something more. And it's all going towards that entire connected factory, straight from designing of new equipment, let's say, all the way to customers and then coming back.
Thanks, Lakshmi. Again, I sense that the same theme that is being emphasized, which is the idea of actually scale, going from end to end, this entire connected factories, which is not just the manufacturing, how does it connect to business? I think that's something that's interesting. What I want to hear from Sridhar is there are big technologies. We have been talking about data analytics from quantitative point of view, but there are a lot of image-based sensing that as a lot of developments, and maybe you can gather data not just about let's say images, but also about textual information that's presented in design documents and so on. How are these being leveraged or leverage them in such solutions for information? I know we work in some image-based things, and I'd like to talk about that. Thanks. So, traditionally, engineers in the digital and measure flow, temperature, pressure, and so on.
as you can there's a lot of other kinds of information that is available. Image, text, sound, as Sridhar mentioned, we have vibration and sound data, which is used as prognostic and diagnostic indicators. Text, now we can combine large amounts of data. So the recent buzzword has been in ChatGPT, which works with very large language models, which helps you to answer questions and so on. But there was, so how do we exploit these to mine existing data? Can we discover rules? There are reports of literature which say they discovered physical rules, laws of physics, laws of chemistry from existing published data. That is one challenge. That is a very interesting development because that allows people to maybe, as also Raj mentioned, can we short circuit this time that we need to spend in the lab? Can we discover information by mining huge amounts of published data, huge amounts of image data, and maybe in the future other kinds of data also, like sound, vibration, or as far as image is concerned, why only stop at visible? Now we can have access to hyperspectral data which goes beyond the visible range. So we have sensors. For instance, the camera over there, most of these cameras can have these detectors are sensitive to non-visible wavelengths also. It's except that they have physical IR filters because that's as far as interpreting images, you are interested in the visible range itself. But what if we could repackage this existing camera to do good quality detection, the chemical composition detection? So this allows you to work with not just visible data, visible spectrum data, but hyperspectral data. Likewise, maybe sound or even, let's say, weather data. Can you weather data? Nowadays, a lot of these weather models are available. And can you fuse these weather models with localized weather station data to predict ambient temperatures over the next 3 or 4 days in a very hyper-local environment, because that might have a significant impact on your plant operation.
Thanks, Sridhar, for bringing that up, because I just wanted to mention one application where weather data, we work with the foundries, sand foundries, that the production of the sand molds actually depends, it depends significantly on the year in which this is made. So there are a lot more different products made during certain times of the year than another time, because of the humidity levels in the atmosphere. Because the blend strategies are not changing depending on the weather. So if you have weather information, you can actually exploit it in order to change your process conditions or the mixture, the way you blend to produce the sand molds in order to reduce the defects. You have a classic case where information, extraneous information outside of the process that actually be leveraged into the productivity. So the second thing that I want to raise, and I know that this has been already in the industry, but then we see the kind of requirements that the industry wants. I mean, what kind of resources do we need in this whole requirement of leveraging AI and analysis, because this is not traditionally a part of the chemical engineering. Are we doing it with chemical engineering? Are they doing it with computer science people? What the kind of resources are they exploiting? What tools did they actually throw some light on this? I just want to again start off with Lakshmi on how are they finding the resources and what kind of resources are they using?
So this is actually a big pain point for me, because getting into project and the process domain and not having the right resources is a huge challenge. Traditionally, what I find in industry is that most of the data scientists, there is, domain is very undersold. And I've met young college graduates who say, I want to do data science and separate domain. But I'm really not being able to pluck these two away from each other, because the application is very domain centric. And it continues to be so in the process industry. So, unless the students have a reasonable amount of interest, unfortunately, a lot of times people say, I'm done with the room after 4 years of engineering. Unless there is a reasonable interest, we find the practice of deployment that much tougher. But, as far as the math is concerned, build a regression equation for this particular data science problem, anyone can do it. So I don't know whether I answered your question. It would have been, just so nice to have people who have a good blend of the domain and, the data science capabilities, but that's very rarely the case.
I agree with Lakshmi. So again, I share with you something which I experienced firsthand when I moved back to India about 8-9 years ago. So I was invited to do a day-long workshop for the C-suite people in a big oil company. After, all 7 hours, they said, all this is fine. So you've got the overview of all AI can do. Can you tell me why is a chemical engineer talking about AI? Right? Why is it not computer scientist who is giving this course? So that was 7-8 years ago. And now I think when I speak with similar customers, the question is now asked in exactly the innovative way that they say, if you're going to develop this model, have you done exactly the same kind of application for another player in our industry? We don't care whether you are AI expert or not. If you have done alarm management in a refinery, we're happy to hear about alarm management from you. So I think the question of does domain play a major role? It seems to me that, unless you understand math, finance, balance, etc., it's difficult to do a life given something happens to alarm management, which may otherwise look like a pure data analytics.
So I agree with both these speakers. So basically, my biggest challenge is my vice presidents and my C-suite people who are not yet open to the fact that the several things, analytics and modeling can help the business. Yes, so what I've done is I took them to a workshop on basically data analysis, and Ram Charan, the strategy guru, he was there. And so one of the things he said was that the business side should always lead the problems. I mean, define the problem statement clearly, define what exactly they're looking for, and then the data scientist comes in to support and find a solution to that. What was happening in our case was the person, we call him IT, but he covers everything from network, hardware to AI. He was driving the process and he was pushing it down the throat of people because he's aware of the changes that's happening. And so one of the things that I told in the beginning also is educating ourselves. The world has changed. So we are rolling out various workshops to open up the mind of people, and then data scientists supporting. Then they will feel much more welcome, and then the problems will get solved faster.
Just want to see that anything to add. Okay, so if we're talking about one of the ways, if you open construct phenomena textbook, which is one of the first textbooks, courses that anyone does, it's very intense and differential equations. And to prepare students to do that, they do a lot of math stresses before. So I think now it's the time is time to make all of these stresses also data intensive. So when they prepare them with additional data science stresses, basically statistics, regression, model building, and so on. And we also include a lot of, just as differential equations are included in the lab in the curriculum. Maybe it's also good in every course, for instance, reaction engineering, construct and so on. Maybe it's also a good idea so that to introduce model building or analysis of data. So rather than just present these correlations, maybe it's a good idea to also expose the students to the raw data, the primary data, and encourage the students to do the derive or come up with correlations. And then if you take a chemical engineering correlation is one of the things that we notice is we use dimensionless numbers to a large extent. And I think the physical implication is that once you use these dimensionless numbers, they are amenable to extrapolation across materials, across geometries, across time scales. Now, the challenge would be with a purely computer science person and without any domain knowledge, would be able to with a model which has very good interpolation capabilities. But we would be able to build a model with similar correlation with extrapolation capabilities. So then that's how you try to bring in the domain knowledge
and the appreciation and the need for data analysis and model building at a very early stage.
Sorry, I just wanted to add one more point. You know, it's a very traditionally run industry, and typically when we go and meet clients like you, there is an expectation that you will bring a lot more of the domain. So I'm not a practicing data scientist like the three of them, but I bring a lot of domain, and that becomes kind of imperative in every conversation that we want to have because clients insist on that. It's a fairly traditional run space.
It's good to hear because one of the fears that we have is whether the narrative is being hijacked by computer science people. When we have of AI on it, where is the domain that so no students can rest assured that not that the thing I hear of everybody is without domain knowledge, it might be difficult to convince that you are capable of solving the problem. Second, domain must bring about a certain amount of generalization capabilities that otherwise pure applied mathematics will never solve. Like in the way you build their correlation. Financial numbers are not something that typically non engineering students would actually know the correlations. They would just, YouTube was like the model, we don't really know dimensionless. So these are aspects that one can learn and can use, and it's like here. So the third thing that I want to just lead off from here is the kind of changes or impact it has on the engineering. How do we achieve what we modify, what we modify, how and so on. So I just must start with the academic thing and then shift to actually what the industry expects of us. So again, I'll ask Raj to take a lead in this and say what he feels to be done to the curriculum itself to these two ideas. So that's a deep question. I'm not sure if I can speak with the curriculum in its entirety. I think there are perhaps a number of fundamental things which are at play in how people learn. I think increasingly people are getting used to learning just in time. That is not the way that we have typically learned in higher education particularly. And therefore, I think people have to get adjusted to that disconnect, but I don't want to speak to that in any great length. I want to just talk about the data aspect of it. So we have math covered in a fair amount of detail in our first couple of years in the engineering curriculum, the chemical engineering in general. But much of that has a very theoretical emphasis and less on connect with the real world. If we were to use, problem-based learning or other kinds of techniques where we, for example, I think I remember a case where was attending a guest lecture in a college. I will not name the college. The lecturer came in with ice cream for every student. He allowed them to, have a go at it for the first couple of minutes. And then he said, how do you make sure that the vanilla doesn't melt before the chocolate on the outside, right? The idea is to motivate thermodynamics by giving them something that they can relate to before bringing in this concepts of thermodynamics or rate of reaction and so on. We need to do something similar with data. If we're talking about chemical engineering particularly, I don't know if any student has gone to a chemical plant before they, or even when they start their bachelor's program. So we would give them a data directly from the plant, that's probably not the way to go. But we would give them data, perhaps some small scale studies that we can do. So instead of doing detailed chemical engineering experiments in the third year, maybe some simplified experiments have to do in the first semester, second semester. So they get an idea of, again, mass balance, energy balance, what have you. And then generate data, allow them to play with data, apply it in their math courses, and then things will follow from that time. Yeah. Okay. So, the question I want to actually focus only on the undergraduate education at this point. The higher level education, at least in here, this is a moment of time. But between 10 years before I graduate, so just give me time to actually sample if you ask for the way expertise as well as AI expertise. So I'm assuming that the industry people looking at the skills and skill level to their employees at just beyond UG or masters. So what are the expectations of the new kind of people that they want to actually what's in the process? Whether they can actually start utilizing these skills, advanced skills in there, and even want to,
Now, firstly, I've always been very thankful that I studied chemical engineering because even in the steel industry, process control, I was in process control systems before. You have a good sense of everything. I mean, we have studied processes, systems engineering projects. We know enough about everything. Only one area where I still have a black hole is electrical. Like, so in electrical, if it comes to this one, that one, I just can't understand what he's trying to say. But generally, we have a good basic understanding. I think in terms of areas where I think it would help, I don't know if it's already there. A little bit of presentation, the soft skills part, where you're able to conceptualize an idea, present it, and elaborate it clearly. That skill would be useful. Definitely interning in real time, I mean, in plants, that would help. And there are, compared to earlier days, today there's a lot of opportunity, and somehow I know Pushpanam is always been pushing me. So I'm now ready to take some interns. So we can give you some short-term, long-term problems. Some you have to solve on the spot, some you can take back and work, but mostly it's on site. So I think a mix of all that would help.
One of the constant problem that we always ask is, what can we sacrifice? You add something and subtract something. Is there something that we can subtract? Now, one of the things is a lot of tools are now being used to solve these AI and health problems and so on. So if we have to actually teach people to use a tool, like we are doing in the simulation lab, we ask them to do simulation exercises. Then what do we can potentially cut out? We think that there are areas where we can kind of things, and then we can introduce these tools for image processing or that's something that we will do.
Definitely, I mean, so I'm sure you have become did one maths course every semester, so the same maths courses, 5-year course. Yeah. Yes. So we've gone from 10 maths courses to 2 or 3 maths courses. Like as when I was a student, we had 3 maths transfer courses, and now we have 1 or 2 maths transfer courses. So the idea seems to be that certain tools are getting commoditized and generalized. So we like to see what concepts or practices and engineering curriculum can likewise lend themselves to easy commoditization or generalization, so that we can spend a little bit more time introducing some of the other unconventional state-of-art techniques and image processing. So that is scope. It's a zero sum game, because at the end of the day, the student has 4 years, and with the number of courses we have this discussion in our academic settings also, right? I mean, what is the number of courses that they need to do? From each the subdiscipline, science, engineering, maths, and application practice. So that's a trade-off, and we have to. It's not easy, but we will do this 10-year curriculum revision every 10 years. So maybe at this curriculum revision, we'll have to look at these things in more detail. Thanks.
That's right. So one thing that we also worry about in this area is a significant amount of programming effort that is required sometimes to actually solve problems in analytics and so on. Not just the math background, but also the programming, because it has to be packaged in some form. One of the things we noticed. So what is the expectation of industry is whether a chemical domain experts to also have substantial reasonable amount of programming ability in order to enter the stream, or we actually have a team where programming and other aspects can be taken care of. Some of the people and collaborate together in architecture solutions. How is it actually done in the industry today?
So now and I'm talking about my company, industries become so specialized that you have very specific verticals for, data science, data engineering, application development, and so on. So the expectation is not that you know end to end of everything, but what you need to know well, and especially when you come as a solution provider for the process industry in the area of data science. At least the context has to be very clear. My biggest, or where I find the biggest blind spot is in the contextualization. So most engineers are very good from an Excel sheet into an application. They are able to take that entire journey very, very comfortably. But talking to the client, understanding, if the results are coming like this, why is it not practical in the industry that I'm talking about? The explainability, all that requires a lot of domain. And that is where people are shying away from. Unfortunately, the ability to retain good talent within the AI sector from chemical engineering is very difficult, because the learning or the soaking in of the domain is something that takes a lot of time. And youngsters today have not shown that much patience as we had. We were able to go and work in an industry. I'm very glad that internships are happening. I hope more and more people get the exposure to industry. They understand what exactly industry wants as they get into the solution.
So you are saying that one need not worry so much about the programming and the domain expertise is what we are looking. If they say they are coming as a chemical engineering expert to solve process engineering problems.
Yes, that is where industry really needs a lot of people, and unfortunately, I don't even see a pipeline.
So I think we are kind of, reaching a time where I would like to actually ask, hold open to the audience and to raise whatever questions they want, and then hopefully our experts will be able to provide some answers and queries. So, over to the audience. Yeah.
Shankar, recently I met an alumni. He talked about programming mobility, so just number 2 minutes. So I met an alumni department. He said he spent about 3 months writing the program. He wrote and then kind of validated and then and other bugs he solved it and then he successfully did that. And then he went to this chat GPT and he said that he solved this program. Within 3 minutes, it gave a program with his error free and words, and then was happy with that program, whatever you got from there. So I don't know whether trying back to solve this problem or is available program done by the machine and then it's using from maybe the learning they can do something else, so we would still help with our teaching programming and learn.
So someone from the team. So the question is whether they are able to solve problems utilizing AI tools that are coming up, just like ChatGPT. Would that, from an industry point of view, is it acceptable, or what is your comment on this?
Are you saying that using a search source like ChatGPT, you have a model or a solution, will we be happy to implement? I don't know. Basically, we would not risk trying out something on the main production platform without having some, what shall I say, rigorous testing of the model or whatever it is. How it came, the solution, we're not that fussy about yet. I don't know I know what ChatGPT can do to some extent, but as you said, it's not a one-man effort, it's a team effort. Normally, there are some domain people, there are people familiar with the root cause of the problem and some with the coding experience. So together we come up with a solution. I don't know. I cannot answer your question clearly.
But there are a lot of requests which are coming from clients that say, can you integrate ChatGPT into some area of work that is of interest to us? And we feel that that is a good way to accelerate. Of course, with some curation, with some governance, on what ChatGPT is actually delivering. But we are not threatened by that. And in fact, it has become a good vehicle for us to accelerate some of the things we want to get done.
So I know from a academic point of view, if I were to give a question exam paper, I would say use ChatGPT to answer. Obviously, that's not a satisfactory. So I try to understand what is permissible from an academic point of view, what we believe will be non-permissible from an academic. So I'll go back to this session here. So when you're starting a PhD, in order to write a back propagation algorithm, which is one step in building a neural network, it will take us 3 months. And you really have to be, fairly well versed with C and good to optimize it in order to be able to get a reasonable performance. Nowadays, I think it's one function call, and you probably can try 20 different options, not just plain vanilla platform. So we are able to now think beyond writing a backpop algorithm and think about how to formulate a problem as a neural network, as a problem that can solve the neural network. To me, it looks like ChatGPT is also giving us just one additional level of aggregation, in the sense that instead of writing the entire program, I can ask the ChatGPT to give me a first job. I would say consider the first job, and I have to, go to it to confirm that it does what I want it to do. But then it makes me more efficient. So that's the way I see it. And from that point of view, I don't say anything bad. Then
so likewise, again, to take the standard equation numerical techniques, you spend a lot of time teaching how to solve linear equations. And I've done that. I've taught several students, and I've told that you never ever write a code to solve linear equations on your own. As Raj mentioned, it's a one-line that's like you and MATLAB to do. That's so new piece. That doesn't mean that the concepts are redundant. But again, the ChatGPT that Raj mentioned is going to be one more layer on top of what we have today. Initially, we had people are working with punch cards, and we work with computers, faster computers, and we actually wrote programs to solve linear equations using function calls. So now maybe ChatGPT gives you version 1 or version 0 of the program. You work from there. We've come a long way. When I studied here the first time, Professor Anand, he in the thermodynamics exam, he said it's an open book exam. You can go anywhere in the campus, provided in 3 hours to come back and get the paper like you were taught. and still as hard as to answer it, even though it was open book and more. Yeah, I think that's interesting. I think because I think his practices is right in this retirement, I think, and many of us who actually conduct only is open to say you bring anything you want. The knowledge is not restricted. You don't have to memorize, but how you utilize it is the thing. So the question is now you frame the question that allows them to utilize these advances in an effective manner. That's a skill that you would find inculcated in students, and we got to see that none of the party members or the industry people feel threatened by these advances, but they believe these are enablers, and that's the good way to kind of regard these advances, I suppose. Yeah, that's the message that's coming. Any other questions? I mean, from
this question is to Lakshmi Ma'am, and this is regarding the implementation of dashboards for monitoring KPIs. As we know that in all chemical engineering plants, we measure the performance of the plant by monitoring the KPIs. So it is very easy for implementing dashboards in new plants. So what are the hurdles faced while implementing dashboards in legacy plants like plants? Therefore, almost like 40 years, 50 years, because one of the roadblocks is if you don't have measurement devices, it's very difficult to measure the KPIs. So in that case, what sort of strategy was being followed while implementing dashboards
to monitor the KPIs, because KPI is a number that when we start showing that we bleed in terms of dollars or rupees, then we easily we start, taking action, corrective actions to bring the KPI back to the track. So the question is, what are the challenges we have to face while implementing dashboards in our own plans?
So you're very right, when it comes to KPI metrics generation, the maturity of the organization is definitely something that we have to understand, right? So some of them are pretty early in the whole digital journey. So it might actually be a legacy unit using just analog instruments, digitalizing those plants, building the pipeline of data that can actually feed into through your PLC into an MES or a data lake. Now, why we move it into a data repository is also to hold a single source of truth, right? Because from a process plant, a utilities plant may say that you are providing so much steam and water to a certain unit, but your unit balance itself may be something different. So you have to ultimately make sure that all this data is, holding a single source of truth, using that for metrics generation. And ultimately, when the metrics come, also you have to align with the people. What kind of metrics are relevant? What kind of assumptions? What kind of periodicity of generation of these metrics need to happen? Whether it's real time, whether it is in a certain cadence that needs to be reported. So all that is very, very important. And we have also seen the power of insights generation. Besides the regular KPI, KPI is like those basic numbers, but dashboarding itself is a very powerful exercise, and that is why many organizations they have a very strong consulting BA, business analysts who look at data and who say, in how many ways can you read more than what the plant is reading, right? So I just, in the interest of, you can tell me if I'm overshooting the time. So there was one project where we had to measure fuel efficiency numbers in connected vehicles. So we did that. Fuel efficiency was just a KPI, right? But when we started getting the data, we started looking at, okay, so 5-year-old vehicle has done so many miles, this particular variant of this particular model, right? What is the typical efficiency number? What kind of engines are being used in that? What kind of manufacturing setup did it come from? What is the maintenance history? So there is a lot of additional insight that you can build into this dashboard. I think to our clients, that is a bigger thing. KPIs is just the MVP that we provide them.
Any other questions on? So, okay, so since we're running out of time, we'd kind of thank all the analysts for a very interesting session. We have highlighted a lot of these issues. I'd like to request I consulted with her, take one also. Yeah. Gone. Go out of the campus, qualifying is a strict thing. Thank you very much for the entire session. So we announced earlier, the engagement closed at 4:45 to 6:30. The chief minister is coming in and going on. So if you, the C sir, and you have your set apart 1 hour for interacting with the posters and students. So you're welcome, stay back. We will engage you from 6:30 here. We will take you on a department wherever you want to visit, whichever lab you want to visit, we can arrange that. So no problem. We are here for the rest of the evening. So if you have to leave, I think please ask one of us something which work will take an hour. We can help you. But please, sir, and welcome you all to interact further with the faculty and students.
We will, one of the things that we also want to do is to follow up on this event. So we will send you a feedback. So all, whatever more interaction and what kind of discussion topics and methodologies, what more of engagement is more effective. So we will follow up with one or two events within the next few months. So from the registration information, we will send you feedback to get more information. We will contact you again on that. And if you have any specific feedback, please feel free to send it to one of us, to me or to any of the organizers that you know. We will take that up. So we definitely want to keep you as a continuing engagement, not just the one-off commemorative event. So we in best interest of both the worlds, like in our industry, will survive with each other. Thank you very much. I think we'd like to have a group picture if possible. We can come closer to the stage before we go to the tea and I think we can get on to the stage.